14 suns share a single piece of cosmic real estate. This is not science fiction, but the staggering reality of a Quattuordecuple star system, a place where 14 stars are locked in a single, intricate gravitational dance. It is one of the most extreme and mysterious configurations we have ever found in the cosmos. By the end of this journey, you will know 50 strange discoveries that rewrite the rules of star formation, orbital mechanics, and reality itself. How could such a system form without tearing itself apart? And what bizarre secrets do these stellar families hide? What do you think happens when gravity writes a symphony for 14 players? The first and most profound discovery is that these systems exist at all. For decades, the very idea was considered a theoretical impossibility, a fantasy of gravity pushed beyond its breaking point. The mathematics of orbital mechanics, the elegant dance of 2 or even 3 bodies, becomes pure chaos when you add more players. Simple calculations suggested that any group of stars beyond a handful should be violently unstable. One star would inevitably be flung into the void, or a catastrophic collision would reduce the system to rubble in a cosmic blink. So when evidence began to point toward not just 10, but 14 stars bound together, the astronomical community met it with deep skepticism. It was like hearing a report of a perfectly balanced house of cards built in a hurricane. The laws of physics, as we understood them, seemed to forbid it. This forced a revolution in detection methods. Astronomers could not simply point a telescope and see 14 stars neatly arranged. Instead, they became cosmic detectives, sifting through mountains of data from observatories like Gaia, which maps the precise positions and motions of over 1 billion stars. They looked for subtle tells, like a group of stars moving in perfect lockstep across the galaxy, their light spectra telling the same chemical story. Finding a Quattuordecuple system was not about seeing a bright, obvious cluster. It was about identifying a statistical ghost, a family of 14 all traveling together against the immense backdrop of the Milky Way. That moment of confirmation, when the data left no room for doubt, was not just a discovery. It was a direct challenge, a message from the universe that our models of cosmic order were far too simple. This defiance leads directly to the second strange discovery. These systems shatter the cosmic rulebook for how multiple stars are supposed to organize themselves. For nearly all the double, triple, and quadruple star systems we know, a clear and stable pattern emerges, one astronomers call the hierarchical model. Picture a set of Russian nesting dolls. At the smallest scale, you have 2 stars locked in a tight, fast orbit around each other, a binary pair. That entire binary pair then orbits as a single unit, with a third star at a much greater distance. That new trio might then orbit as a group, with a fourth star even farther out. Each layer is neatly separated, with clear, stable orbits within orbits. It is a gravitational architecture designed for long-term survival, keeping the stars from getting too close and triggering chaos. This is how we believed all complex systems held themselves together, through orderly, nested hierarchies. But Quattuordecuple systems laugh in the face of this neat arrangement. In some of these 14 star families, the hierarchical model breaks down completely or becomes so twisted it is barely recognizable. Instead of clean layers, we find stars occupying what should be unstable positions, dancing in paths that cross and weave through each other in seemingly reckless ways. Imagine 14 dancers on a stage, not performing in separate, coordinated groups, but all moving in one immense, interconnected, and constantly shifting pattern where any dancer could, at any moment, swing past any other. This is not a nested Russian doll. It is a complex mobile where every piece directly influences every other piece. Astronomers have found evidence of stars in these systems that are neither in a tight binary nor a distant, stable orbit, but are instead caught in a complex gravitational resonance between several other stars, tracing figure 8 paths or occupying temporary Lagrange points in a constantly rebalancing act. This discovery forces a troubling and exciting question. Are we looking at a system that is momentarily stable on its way to a violent rearrangement? Or have we discovered an entirely new, ultra-complex form of gravitational order, one that our simple models of hierarchies cannot yet describe? The very existence of these systems presents a third, deeply unsettling mystery, one of cosmic violence and missing family members. Astronomers call it the runaway star problem. Within the dense, crowded nurseries where stars are born, gravitational encounters are not gentle dances but brutal shoving matches. When two binary pairs pass too close, their intricate gravitational fields can interact like slingshots, violently accelerating one star to incredible speeds, ejecting it from its home entirely. These runaway stars, cosmic orphans flung into the dark, are a known phenomenon, but within the context of a Quattuordecuple system, this process takes on a terrifying new scale. The strange finding is that some of these 14 star families show clear kinematic scars, evidence that they are not complete. By meticulously tracing the motions and energies of the remaining stars, astronomers can sometimes work backwards, like forensic scientists reconstructing a crime scene. They find that the current orbits of the 14 stars only make sense if there were once 15 or even 16. The math reveals a ghost, an empty slot in the gravitational architecture where another massive object once resided. The orbits of the survivors are often slightly perturbed, tilted, or more eccentric than they should be, all pointing to a moment of profound trauma in the system's past. This suggests a staggering event, a gravitational catastrophe where one or more stars were not just nudged, but violently kicked out at speeds that could send them clear across the galaxy. What remains is not a pristine, untouched family, but a group of survivors, their motions forever marked by the loss. This forces us to ask, were these systems even more extreme at their birth, perhaps starting with 16 or 18 stars before a period of gravitational purging left the 14 we see today? The system we observe may be the stable, quiet aftermath of a stellar war, a ceasefire held in place by the terrifying memory of what happens when gravity turns destructive. This gravitational ceasefire is held together by a fourth discovery, a phenomenon of such precise cosmic harmony it borders on the impossible. We are talking about orbital resonances. In our own solar system, we see a beautiful, simple example. Pluto orbits the Sun twice for every 3 times Neptune goes around. This 3-to-2 resonance is a gravitational agreement, a repeating pattern that keeps the two bodies from ever getting too close and disrupting each other's paths. It is a stable, two-body clockwork, but within a Quattuordecuple system, the concept of resonance is stretched into a form of celestial art that defies belief. Astronomers have detected not simple pairings, but intricate chains of resonance involving 4, 5, or even more of the 14 stars. Imagine a symphony where every instrument is a planet-sized sphere of fusing hydrogen, and their orbits are the notes. In these systems, you might find a chain where star A completes 5 orbits in the time it takes star B to complete 3, star C to complete 2, and star D to complete 1. Their orbital periods are locked together in a precise, stable, multi-part mathematical ratio. This is not a coincidence. It is the universe's most complex gravitational feedback loop, a self-correcting mechanism where each star's gentle tug helps keep all the others in rhythm. The sheer stability of this arrangement is what baffles theorists. When they try to simulate these multi-body resonances on computers, even the most powerful models often fail. Over millions of simulated years, these delicate dances tend to fall apart, descending into the predicted chaos. The fact that we observe them in reality, persisting over cosmic timescales, means there is a stabilizing factor our equations are missing. It suggests these stars are not just in resonance. They are in a state of super-resonance, a configuration so finely tuned that it somehow absorbs the tiny gravitational nudges from passing stars or interstellar gas clouds without breaking the pattern. This discovery turns the system from a mere collection of stars into a single, coherent gravitational organism, a clockwork of 14 parts ticking in unison against the silent backdrop of deep time. The clockwork stability of these systems suggests an ancient origin, a family that has had billions of years to settle into its delicate rhythms. Logic dictates that such a complex gravitational ballet must be the product of immense time, a system that has dynamically relaxed into its current state after eons of minor adjustments. This assumption is the fifth discovery to be completely overturned. Some of these Quattuordecuple families are not ancient cosmic elders, but stellar infants, astronomically speaking. They have been found not in the quiet, empty reaches of interstellar space, but still embedded within the violent, dusty wombs of their stellar nurseries. These are regions like the Orion Nebula, but on a far more extreme scale, where gas and dust are still collapsing, and new stars are igniting all around them. To find a system of 14 stars already bound together in such a place is like walking into a chaotic, bustling maternity ward and finding a perfectly synchronized choir of 14 newborns. It defies every standard model of star formation. The traditional story goes that a large cloud fragments into many pieces, which then collapse individually into stars that drift apart or form loose, unstable clusters. Over millions of years, gravitational interactions eject most members, leaving behind a stable core. But here, the stable core of 14 appears to have formed almost instantly, before the nursery itself has even finished its work. This forces two radical and equally mind-bending possibilities. The first is that these 14 stars form together in place, a single monolithic cloud that somehow fragmented directly into this precise, stable configuration from the very beginning. This would require a starting density and angular momentum so perfectly tuned, it seems like a cosmic miracle. The second, more violent possibility is that we are catching the system in the act of a recent rapid assembly. Perhaps several smaller groups of stars, triplets, and quadruplets that formed separately, recently sailed too close to each other in the crowded nursery. In a brief, furious episode of gravitational capture, they became tangled together into this new 14-star family, their orbits still settling from the trauma of that encounter. If this is true, then the intricate resonances we see are not the product of billions of years of refinement, but a startlingly quick gravitational truce, a ceasefire established in the cosmic blink of an eye. Either scenario reshapes our understanding of how stars are born, suggesting that the universe can produce finished, hyper-complex masterpieces in a single, rapid stroke of creation or catastrophe. The presence of these infant systems leads to a sixth, heartbreaking discovery, one that searches for the ghosts of worlds that never were. If 14 stars can form and survive in such a tight, chaotic gravitational embrace, could planets? The very idea seems absurd. The gravitational tides from so many nearby suns would stretch and pull at any forming protoplanetary disk, scattering the dust and gas before it could ever coalesce into a stable world. The stable orbits required for a planet, even around a single star within the group, would be nearly impossible to find, a tiny safe harbor in a sea of relentless stellar gravity. Yet, when astronomers point their most sensitive infrared and radio telescopes at these Quattuordecuple systems, they find something astonishing. Around several of the individual stars, they detect the faint, telltale glow of warm dust, the signature of a debris disk. This is not the smooth, primordial disk where planets are born, but the aftermath of destruction, a ring of rocky and icy rubble. Think of it as the cosmic equivalent of an asteroid belt, but one that tells a tragic story. These debris disks are the evidence of planetary systems that try to exist here. The dust is what remains of countless planetesimals, the building blocks of worlds that collided and shattered under the relentless gravitational stress of 13 other suns. It is the glittering aftermath of a construction site that was demolished before the skyscraper could ever be completed. In some systems, the chemical fingerprints in the light from these stars add another layer of mystery. They show unexpected abundances of heavy elements, metals that should have been locked away deep within rocky planets. Their presence in the stellar atmosphere is like finding bricks and mortar floating in the air above a demolished building, a clear sign that solid, terrestrial material has recently fallen into the star. This points to a cataclysmic event, perhaps the final death spiral of a fully formed planet that had its orbit destabilized, dragged down into its sun by the combined pull of its stellar neighbors. So the choice is stark, and both possibilities are profound. Either we are seeing the graveyard of planets that managed to form against impossible odds, only to be torn apart in a later epoch of instability, or we are witnessing the sole, battered survivors of that destruction, the last remaining debris rings from systems that were once far more complete. This means that within these 14 sun families, there might have been, for a fleeting cosmic moment, not just stars but entire worlds, places with 14 sunrises painting their skies, before the gravity that created them ultimately turned and destroyed them. The tragedy of these shattered worlds points to an even deeper mystery within the family itself. Among the 14 suns, a strange and unbalanced hierarchy emerges. In most star clusters, you find a range of masses, a natural distribution from heavy to light, like a family with parents, teenagers, and children all living under one roof. But in these Quattuordecuple systems, astronomers are finding something far more bizarre. They are discovering families of extreme inequality, where one sibling is a giant and the rest are dwarfs. Picture a household not with a range of sizes, but with one professional basketball player over 7 feet tall, living with 13 toddlers. This is the scale of the disparity. The most common stars in the universe, and often in these systems, are M dwarfs. These are small, cool red stars, often only a fraction of the sun's mass and brightness, burning their fuel with a frugal patience that will let them shine for trillions of years. They are the quiet and numerous background population of the galaxy, yet in the same gravitational embrace, sharing the same origin story, astronomers have found a stellar outlier, a behemoth. This is an O-type star, a true cosmic titan. These stars are monsters, dozens of times more massive than our sun, burning with a ferocious blue-white intensity. They live fast and die young, pouring out torrents of ultraviolet radiation and stellar winds with the force of a hurricane. Their very presence in a fragile 14-star family is like finding a lit fusion reactor at the center of a house of cards. The discovery of such an extreme mass ratio is deeply puzzling. How could these stars possibly be siblings? Standard star formation theories suggests they all condensed from the same cloud of gas and dust. If that cloud was rich enough to form one O-type star, it should have been capable of forming several other massive stars alongside it. You would expect a family of giants, not one giant and a crowd of runts. The existence of this lone titan forces astronomers to reconsider the very birthing process. One compelling yet violent explanation is that the massive star did not form peacefully alongside its siblings, but through a process of stellar cannibalism. In the crowded, dense core of the stellar nursery where this system was born, the protostars, the infant versions of these suns, would have been surrounded by their own disks of gas. In such close quarters, the most massive infant with the strongest gravity could have begun to violently steal material from the disks, and even the forming bodies of its smaller neighbors. It gorged itself on their birthright, growing to monstrous proportions while stunting their growth, leaving them as permanent dwarfs. This creates a disturbing image of the system's infancy, not as a cooperative nursery, but as a ruthless competition where the biggest sibling consumed the resources meant for the others. Its incredible power a direct result of their deprivation. The other staggering question is how the smaller stars survive the Titan's wrath at all. The moment an O-type star ignites, it floods its surroundings with a sterilizing blast of radiation so powerful it can blow away the remaining gas in a nursery and strip the atmospheres from any nearby planets. For a dozen fragile M dwarfs to remain in a stable orbit around such a fury seems impossible. Their very existence suggests they formed at a specific, sheltered distance, or that the system's complex orbital dances somehow keep them in protective gravitational pockets, swinging close to the giant only briefly before retreating to safer reaches. This lone, brilliant giant, shining amidst its many faint red siblings, is not just a star. It is a monument to a violent and unequal childhood, a king whose throne is built upon the stolen potential of its family. This inequality among siblings forces us back to the very beginning, to the moment these 14 stars were born. Our leading theories of star formation paint a beautiful but seemingly simple picture. It starts with a vast, cold cloud of gas and dust, drifting silently in the interstellar dark. A trigger arrives, perhaps the shock wave from a distant supernova or the gentle pressure of a passing spiral arm. The cloud begins to collapse under its own gravity, fragmenting into smaller and smaller clumps, like a droplet of water breaking apart in midair. Each of these clumps continues to collapse, spinning faster as it shrinks, forming a central protostar surrounded by a swirling disk of leftover material. From this disk, planets may eventually coalesce. For a double or triple star system, the theory adapts elegantly, suggesting the initial cloud fragmented into 2 or 3 main clumps that remained gravitationally bound. But when you stretch this elegant process to explain the sudden, simultaneous birth of 14 stars, all bound in a stable configuration, the theory begins to crack under the strain. How does a single cloud know how to fragment into exactly 14 stable pieces, and not 13 or 15? How do those pieces avoid either drifting apart or crashing together immediately? The existence of Quattuordecuple systems is a direct challenge, a cosmic puzzle that demands we consider far more dramatic and chaotic birth scenarios. One radical possibility is the fragmentation of a supermassive disk. Imagine not a cloud breaking apart, but a single, incredibly massive protostar forming at the center. Around it, instead of a modest disk for planets, forms a disk of gas so immense, so dense, and so massive that it becomes gravitationally unstable in its own right. This is not a placid pool of dust, but a seething, turbulent maelstrom. Within this colossal structure, whirlpools and clumps of gas could collapse directly into new stars, right there in the disk, orbiting the central behemoth. This process, called disk fragmentation, could spawn multiple stellar siblings in a very short time, all sharing the same orbital plane, like pearls forming on a spinning ring. This could explain how so many stars end up in a relatively flat configuration, but it still requires starting conditions of almost unimaginable density and mass to get the process going. A second, more social scenario involves cosmic capture. Perhaps this family of 14 is not all biologically related. Imagine our system starting as a smaller, more typical cluster of, say, 4 or 5 stars. As it drifts through a particularly crowded stellar neighborhood, like the heart of a galactic spiral arm, it has a close gravitational encounter with another passing cluster. In this slow-motion celestial dance, the two groups do not collide but gently intertwine. Their gravitational fields mesh, and several stars from each group become trapped in a new, combined system. This process could repeat over millions of years, with our growing stellar family capturing orphans from other clusters or snatching solitary stars that wandered too close. The result is a gravitational federation, a patchwork family assembled from different lineages. This would explain the sometimes wild variations in star types and ages within a single system, but it makes the achievement of long-term stability even more miraculous, as these captured stars would need to be gently coaxed into the delicate resonant orbits we observe. The third and most violent birth story is one of merger and chaos. Picture a dense stellar nursery, not with one cloud, but with several small, forming systems of triplets and quadruplets all being born in close proximity. The nursery is so packed that these infant systems cannot escape each other. While they are still young and surrounded by extended halos of gas, their gravity begins to tangle. The gas creates a drag, a cosmic friction that saps their orbital energy and pulls them inexorably together. In a relatively short period, these several small families experience a rapid, tumultuous merger. It is less a graceful dance and more a gravitational pile-up. Through this chaotic process, they settle into a new, single, incredibly complex system, a Quattuordecuple star system forged in the collision of smaller families. This scenario of hierarchical merging could naturally produce the twisted, non-nested orbital architectures that baffle astronomers, as the original orderly orbits of the smaller groups are shredded and rewoven into a new, emergent pattern. Each of these theories, the super disk, the social capture, or the violent merger, pushes the boundaries of what we thought possible in star formation. They move us from a model of quiet, isolated collapse to one of dynamic interaction, extreme environments, and gravitational diplomacy on a grand scale. The 14 suns are not just a curiosity, they are a direct challenge, forcing us to rewrite the first chapter in the life story of stars, suggesting that the universe builds its most complex families not in solitude, but in crowds, and not always with peace, but sometimes through a form of controlled cosmic violence. The chaotic violence of their birth leaves an invisible, enduring legacy woven through the very fabric of space around these stars. We must now consider magnetism. Every star, including our Sun, generates a powerful magnetic field, a vast, invisible force that shapes its atmosphere and can erupt in spectacular flares. In a solitary star, this field is a self-contained bubble, a complex web of forces anchored to the star's spinning core. But place 14 of these bubbling magnetic cauldrons in close proximity, and something utterly bizarre occurs. The ninth discovery is that in some Quattuordecuple systems, these individual magnetic fields do not stay separate. They become entangled. Radio telescopes and X-ray observatories have detected signatures of magnetic structures that stretch between stars, linking them like cosmic threads in a spider's web. We are not seeing simple, paired connections, but a messy, dynamic network where the magnetic influence of one star can be felt by 3 or 4 others simultaneously. Imagine taking 14 powerful bar magnets, throwing them into a box, and shaking it violently. The forces would push and pull, snapping together in some places, repelling in others, creating a tangled, unstable mess. That is the magnetic reality inside these families. The cause of this entanglement is a 3-part mystery. The first possibility is a shared origin. If these stars formed from the same dense knot of primordial gas, that material was already threaded with a weak, galaxy-spanning magnetic field. As each star condensed, it amplified that local magnetic flux, but because they all grew from the same magnetic cloth, their individual fields remained fundamentally linked, like branches growing from a single root system. A second, more dramatic cause is close encounters. When 2 stars in the system swing perilously close in their complex dance, their independent magnetic fields can literally touch. The forces can reconnect, a process that snaps magnetic lines and ties them together in new configurations, transferring energy and creating temporary bridges of superheated plasma between the stellar atmospheres. The third and most volatile cause is stellar fury itself. A massive flare erupting from one star does not just blast radiation into space. It launches a cloud of magnetized plasma, a coronal mass ejection. If this magnetized storm cloud washes over a neighboring star, it can interact violently with that star's own magnetic field, temporarily coupling them together. In a system with 14 stars, such events could be constant, a never-ending storm of magnetic handshakes and separations that leaves the entire volume of space within the system crackling with interconnected energy. This transforms the system from a collection of individual bodies into a single, connected electromagnetic entity. The practical effects are staggering. A flare on one star could, via these magnetic bridges, trigger heightened activity on another star light years away within the same family. Auroras on any hypothetical planets would not be driven by one sun, but by the combined, flickering magnetic chorus of many. This discovery reveals a hidden layer of interaction, one that works alongside gravity to bind these 14 suns into a truly unified and unimaginably complex organism. The tangled magnetic web suggests a constant state of stellar fury, a never-ending storm of flares and eruptions. Yet discovery number 10 reveals a paradox so deep it silences the very chaos we expect. Some of these 14 star families are eerily, unnervingly quiet. Logically, this should be impossible. 14 massive engines of fusion, their magnetic fields intertwined, their gravity constantly tugging and squeezing. This is a recipe for perpetual violence. We expect these stars to be hyperactive, their surfaces marred by giant sunspots, their coronae blazing with constant flares, their stellar winds screaming into space at millions of miles per hour. But in certain quattuordecuple systems, the opposite is true. Observations across multiple wavelengths, from X-rays to radio, show stars that are anomalously calm. Their flare rates are lower than solitary stars of the same type. Their X-ray emissions, a direct tracer of magnetic heating in the outer atmosphere, are faint. They seem to be in a state of deep, almost meditative stillness. This serenity is not a sign of old age or low energy. These are often young, vibrant stars. It is a forced calm, a stillness imposed by the very thing that should be causing the storm, gravity itself. The leading theory is one of perfect and terrifying balance. The complex gravitational dance of 14 bodies may create a form of tidal locking on a system-wide scale. Just as our moon is tidally locked to Earth, showing only one face, the immense and perfectly timed gravitational pulls from 13 siblings may be effectively breaking the spin of each individual star. A star's rotation is the engine of its magnetic dynamo. Spin it fast, and you generate a strong, tangled magnetic field that erupts in flares. Slow it down, and the magnetic field weakens, becoming more orderly and quiet. In these serene systems, the gravitational tides may be acting as a cosmic regulator, gently but firmly applying a brake to each star's rotation, synchronizing their spins to their orbits in a grand, stabilizing feedback loop. This creates a precarious equilibrium. The system has found a sweet spot where the gravitational forces perfectly counteract the internal forces driving stellar activity. It is a state of metastable peace, like a pencil balanced perfectly on its tip. The slightest perturbation, a close pass from another star cluster, the subtle loss of mass from one member, could disrupt this delicate balance. If that happens, the braking effect could vanish. The stars would begin to spin up again, their magnetic dynamos roaring to life, and the entire system could transform from a garden of quiet suns into a raging inferno of stellar storms in a relatively short astronomical time. So these quiet families present us with a profound choice. Are we looking at a system that has achieved a miraculous, long-term harmony, a gravitational nirvana where chaos has been subdued? Or are we witnessing the calm before a storm of cosmic proportions, a temporary ceasefire in a war that has been raging since these stars were born? The silence of these 14 suns is not peaceful. It is the silence of perfect tension, a breath held for millennia, waiting for the moment the music of the spheres finally falters. This profound silence is not an end, but a perfect beginning for an experiment of cosmic scale. These quattuordecuple systems have become the universe's most exquisite natural laboratories for testing the very fabric of gravity itself. The intricate, clockwork orbits of 14 stars provide a testing ground so sensitive it can detect the fingerprints of Einstein's general relativity in ways our solar system never could. The strange discovery here is one of subtle drift. Astronomers tracking these stellar dances over years have noticed tiny, persistent deviations in their paths. The orbits themselves are slowly rotating, a phenomenon called precession. In our solar system, Mercury's orbit precesses due to the Sun's gravity warping spacetime, a key proof of general relativity. But in a 14-star system, the effect is magnified and tangled by the gravitational influence of every single member. The predicted precession from Newtonian gravity alone does not match the observed minuscule wobbles in the stellar paths. Something is ever so slightly tugging on these suns, bending their orbits in ways that pure Newtonian math cannot account for. The leading candidate is, of course, the subtle spacetime curvature predicted by Einstein. Each star is not just pulling on the others, it is sitting in a dimple in the cosmic fabric created by all the others. As they move, they roll through each other's dimples, causing those tiny, extra shifts in their orbits. Measuring these shifts across 14 interconnected bodies is like listening for a whisper in a chorus, but it offers a check on relativity with a precision we could never achieve in a lab. Yet there is another, more shadowy possibility for these orbital anomalies. The timing variations could be pointing to something invisible woven through the system itself, dark matter. We think of dark matter as a vast, diffuse halo surrounding galaxies. But what if, on the scale of a star system, it could clump into faint, granular clouds? If a Quattuordecuple system formed within or later captured a dense knot of dark matter, the gravitational pull of that invisible mass would subtly alter the orbits of the stars. The observed precessions could be the first hint of dark matter's distribution on the smallest scales imaginable, a ghostly fingerprint within a family of suns. This transforms the system from a curiosity into a fundamental instrument. It is a massive, natural interferometer testing the laws of physics. Each star is a probe, and their collective motion is the readout. By deciphering their minute orbital waltz, we are not just studying stars, we are conducting an experiment on the nature of gravity, spacetime, and the hidden substance that binds the cosmos. Gravity's grand experiment reveals another layer of strangeness when we look at the family members themselves. We would expect a random draw from the cosmic deck, a natural spread of stellar sizes and colors within the group. Yet Discovery 12 confronts us with a sight so uniform it feels artificial. In certain Quattuordecuple systems, astronomers have found that all 14 stars are nearly identical. They share the same mass, the same temperature, the same spectral class, like a set of cosmic twins produced on a stellar assembly line. This is not a family with one giant and many dwarfs, but a perfectly matched ensemble, 14 singers with precisely the same vocal range. This eerie uniformity defies the standard model of star formation, where a collapsing cloud fragments chaotically, producing a range of clumps that become stars of different sizes. A cloud that fragments into 14 pieces should, by all odds, produce 14 different stars. Finding such perfect equality is like shaking a bag of marbles and having them all land in a perfectly straight line, every one the same size and color. The odds are astronomically low. So how does nature achieve this impossible symmetry? One radical theory points back to the idea of a supermassive disk. Imagine a single, incredibly massive protostar forming, surrounded by a disk of gas so vast and dense it begins to fragment. But instead of fragmenting randomly, this disk might have experienced a phenomenon called gravitational instability in a remarkably uniform way. Think of the surface of a pond just as it begins to freeze. Under the right conditions, the ice doesn't form in random chunks, but in a beautiful hexagonal honeycomb pattern, each cell nearly identical to the next. In a similar way, the rotating disk of gas might have reached a critical point where its own gravity caused it to break apart in a regular, patterned fashion, spawning clumps of almost exactly the same mass and composition. This would be star formation as a precise, geometric process, not a chaotic one. Another, more dynamic possibility involves a brutal form of sibling rivalry taken to its logical extreme. Perhaps the system did start with a natural range of masses. In the crowded, violent environment of their shared nursery, the stars were constantly nudging each other, their gravitational interactions transferring energy. Over time, This could have led to a process of gravitational sorting and ejection. The stars that were too heavy or too light for the group's delicate balance were violently kicked out, leaving behind only those within a very narrow mass range that could settle into a stable, resonant configuration. The 14 identical stars we see are not the original family, but the survivors of a gravitational purge, the ones who fit the system's precise harmonic requirements. This creates a haunting image of the system's past, not as a peaceful nursery, but as a cosmic coliseum where only the most perfectly matched competitors were allowed to remain. The final and perhaps most mind-bending explanation is that we are seeing the result of a shared adolescence. If these stars formed extremely close together, still swaddled in thick shrouds of gas, their outer atmospheres might have literally touched. In this intimate stellar embrace, material could flow between them, equalizing their masses like water leveling between connected basins. The more massive star would feed material to the less massive one until a balance was reached. This would mean these 14 suns did not finish forming in isolation, but grew up literally connected, sharing their substance until they became perfect mirrors of one another. Each of these theories challenges our understanding in a different way, pushing us to consider star formation as a process of geometric precision, violent selection, or profound interconnection. The existence of these identical stellar families asks a fundamental question about order in the cosmos. Is such perfect uniformity a rare accident, a fleeting moment of cosmic harmony, or is it a necessary signature of stability, the only way a system of 14 can hold itself together across the eons? Gravity's perfect symmetry has a violent, shaping hand. Discovery 13 pulls back the curtain to reveal stars that are not serene spheres, but cosmic eggs. Within the relentless embrace of 13 siblings, tidal forces are actively reshaping these suns. Tides are not just for oceans, they are the stretching force of gravity itself. When one massive body pulls on another, the near side feels a stronger tug than the far side. This difference stretches the object. Our moon pulls a gentle tide on Earth's oceans. But in a Quattuordecuple system, each star is simultaneously pulled in 13 different directions by its neighbors, a constant multidirectional tug of war that never ceases. The result is not a subtle bulge, but a profound and permanent distortion. Advanced telescopes using techniques like interferometry have detected stars in these systems that are visibly oblate, stretched into ellipsoid or even egg-like shapes. They are not spinning fast enough to flatten themselves. This deformity is imposed from the outside, a fingerprint of the system's collective gravity permanently pressed into their fiery flesh. This relentless stretching does far more than alter their appearance. It cooks them from the inside. As the star's material is constantly kneaded and flexed by the changing tidal forces, friction is generated deep within its plasma heart. This is tidal heating on a stellar scale, a process we usually associate with volcanic moons like Jupiter's Io. For a star, this external heat source has bizarre and counterintuitive consequences. The first is a potential for longevity. A star's lifespan is dictated by how quickly it burns through its core hydrogen fuel. The extra heat from tidal forces can cause the star's interior to churn more vigorously, mixing fresh hydrogen from the outer layers down into the fusion furnace at the core. This is like stoking a fire with extra oxygen. It could allow the star to burn its fuel more efficiently, potentially extending its life by hundreds of millions, even billions of years. In a system of 14, you could have stars that are chronologically ancient but physiologically middle-aged. their clocks slowed by the very gravitational chaos that surrounds them. The second consequence is far more dramatic and lurks at the surface. In extreme cases, the tidal heating may be so intense, so focused in the outer layers, that it triggers localized and unusual nuclear fusion events. Imagine the star's normal, stable core fusion happening deep within. Now picture additional, sporadic fusion igniting in patches near its distorted surface, fueled by the intense pressure and heat from the tidal squeezing. This is not the controlled burn of the core, but a fitful, flash-fire fusion in the stellar atmosphere. Astronomers search for the chemical signatures of such events' abrupt, temporary spikes in certain elements that should not be so abundant in a star's outer layers. It suggests a sun that is not just heated by tides, but occasionally set on fire by them, its surface sparkling with unnatural fusion flares triggered by the gravitational grip of its family. This transforms our view of these stars from passive bodies to active participants in a thermodynamic drama. They are not just being pulled, they are being stirred, heated, and potentially remade by the perpetual embrace of their siblings. Their very life stories were written by the tides of 14 suns. Their stretched and heated forms are hidden by a cosmic illusion, one that makes the extraordinary appear utterly ordinary. From a truly immense distance, a Quattuordecuple star system does not look like a crowded family portrait. It masquerades as a single, unremarkable point of light in the telescope's eye. The combined glow of 14 suns merges into one brilliant pinprick, indistinguishable from any solitary star in the night sky. This disguise is so perfect that for decades, many of these systems were cataloged simply as bright, slightly peculiar stars, their true nature completely unsuspected. Unmasking them required astronomers to become masters of subtlety, learning to read the faintest whispers in the starlight. The first clue is often a strange and inconsistent color. A single star has a specific hue dictated by its temperature, from cool red to searing blue. But the blended light of 14 stars of different types creates a composite color that doesn't match any known spectral class. It might appear as an odd, washed-out white or a faintly greenish tint that standard models cannot explain. This chromatic anomaly is the first crack in the facade, a hint that the light is not coming from a single source but from a mixture. The next telltale sign is a light curve that defies all logic. For a normal eclipsing binary star, astronomers expect a predictable pattern of dimming, a primary dip when the larger star is blocked, and a secondary, smaller dip when the smaller star passes behind. The graph is clean, rhythmic, but for a system of 14 suns, the light curve is pure chaos. Imagine trying to predict the shadow patterns cast by 14 lanterns swinging on 14 different pendulums in a room. The dimming is erratic, with multiple overlapping eclipses of varying depths happening constantly. A deep fade might be caused by two large stars aligning, only to be interrupted by a shallower dip as a smaller star passes in front of a third. The graph looks less like a tidy heartbeat and more like the scribble of a seismometer during an earthquake. This unpredictable flickering, once dismissed as instrument error or stellar variability, is now recognized as the signature of a deeply crowded sky. The most definitive proof, however, comes from an almost imperceptible dance. Even when their light blends, their gravity cannot hide. Using supremely precise instruments like the Gaia Space Observatory, astronomers measure the exact position of that single point of light over years. If it were one star, its path through space would be a smooth, straight line. But the gravitational center of a 14-star system is a constantly shifting point, tugged this way and that as the members orbit their shared center of mass. This causes the entire system's photometric center, that single point of light, to trace a tiny, wobbling path across the sky, a staggeringly complex pattern called astrometric noise. That microscopic wobble is the ghost in the machine, the undeniable signal that the object is not one massive body, but a hidden swarm of many. It is the universe's confession, written in the silent language of motion. So the star you see tonight might not be a star at all, but a crowded city of suns, their individual identities lost in the glare, their true story waiting to be decoded from the faintest tremble in the void. This cosmic disguise hides a gravitational arrangement of almost mathematical beauty. Within the apparent chaos of 14 suns, astronomers have found a configuration so stable it was thought to only exist in theory, borrowed from the architecture of our own solar system. They are called Trojan points. Picture a massive planet like Jupiter orbiting the Sun. There are 2 points in its orbit, one 60 degrees ahead of the planet and one 60 degrees behind, where the gravitational pulls of the Sun and Jupiter perfectly balance. These are gravitational parking spots, zones of stability where smaller objects, like asteroids, can be trapped indefinitely, sharing the planet's orbit without ever colliding with it. Our solar system has thousands of these Trojan asteroids accompanying Jupiter. The discovery within a Quattuordecuple system is that these stable points are not just for asteroids and planets. They can host stars. In one of these 14 star families, observations revealed a central pair of stars locked in a tight binary dance. But the true marvel lies ahead of and behind this pair. Orbiting the same center of mass at those perfect 60-degree Lagrangian points are not rocks, but full-fledged stars. These are stellar Trojans, massive suns leading and trailing the central binary like cosmic guardians in a perpetual, synchronized procession. It creates a configuration of breathtaking symmetry, a binary pair, with a star eternally ahead in its path and another eternally behind, all tracing the same orbital track around the system's heart. This arrangement is a masterstroke of gravitational engineering. The Trojan stars are not simply following the binary. They are trapped in a delicate equilibrium, feeling an equal tug from both members of the central pair. Their position is stable, but not rigid. They vibrate or gently sway within a region around the exact Trojan point, like a marble rolling slowly back and forth in a very shallow bowl. This discovery solves a piece of the 14-star puzzle, explaining how such massive objects can coexist in close quarters without immediate catastrophe. It provides a template for stability, a way to pack multiple stars into a single orbital lane by using the universe's own points of balance. But it also raises a profound question about formation. Did these Trojan stars form in place, condensing directly from the protostellar cloud at those perfect points of balance? Or were they captured, gently nudged by gravitational interactions over millennia until they slipped into these celestial parking spots and were locked in for eternity? Their presence suggests a system that has either achieved a state of perfect gravitational harmony or was born with a blueprint so precise it included these stellar sentinels from the very first moment. The Trojan arrangement offers a stable architecture, but it cannot hide a deeper chemical schism within the family. Stellar spectroscopy, the art of dissecting starlight into its component colors, reveals a startling truth. When astronomers train their spectrographs on the individual members of a Quattuordecuple system, they expect a uniform chemical signature. These stars were born from the same primordial cloud of gas and dust. a shared womb that should have imprinted them all with the same elemental fingerprint. Yet the data tells a different, more fractured story. In several of these systems, the sibling stars show wildly divergent chemical compositions. One star might be rich in iron, silicon, and other heavy elements, metals forged in the hearts of ancient stars and scattered by supernovae. Right beside it, another star appears almost pristine, possessing only the primordial hydrogen and helium that filled the early universe, with barely a trace of those heavier metals. This is not a slight variation. It is a fundamental mismatch, as if two siblings from the same parents had completely different DNA. This chemical dissonance shatters the simple narrative of a common birth. It forces two radical possibilities, each with profound implications. The first is that this family of 14 is not biologically related at all. Perhaps we are witnessing a gravitational federation assembled from stars that formed in different parts of the galaxy, in clouds with vastly different chemical histories. One star could have been born in a region enriched by many generations of supernova, while another formed in a quiet, metal-poor backwater. Their gravitational capture into this single system would then be a later event, a cosmic adoption that brought together strangers with different ancestral stories. The second possibility is even more dramatic and points to a hidden history of cosmic consumption. If the stars did form together, the metal-rich member may bear the scars of a planetary feast. Recall the debris disks, the graveyards of shattered worlds. If a fully formed terrestrial planet, rich in iron and rock, had its orbit destabilized and spiraled into its host star, the heavy elements from that destroyed world would pollute the star's outer atmosphere. The star's light would then carry the spectral signature of that planetary destruction for millions of years. In this scenario, the metal-rich star is not inherently different from its pristine siblings. It is simply the one that committed an act of stellar cannibalism, consuming the rocky remains of its own planetary system. Its atmosphere is now stained with the evidence, while its siblings, whose planets either never formed or were flung into the void intact, remain chemically clean. This means the chemical diversity within these systems is not a birthmark, but a record of life and death on a planetary scale, a silent testimony to worlds that were built and then destroyed within the gravitational storm of 14 suns. The chemical scars of lost worlds point to a family dynamic of staggering inequality, where even the smallest members can be violently consumed. But what about objects that never quite made it to stellar status? Discovery 17 introduces the cosmic in-between, the failed stars known as brown dwarfs, and places them directly inside these 14 sun families. A brown dwarf is a celestial paradox, an object caught in a gravitational identity crisis. It forms like a star from the collapse of a gas cloud, but it simply does not have enough mass to ignite sustained hydrogen fusion in its core, the defining act that makes a true star shine. It is too massive to be considered a planet, often dozens of times heavier than Jupiter, yet too small and cool to be a star. For most of its life, it merely glows a dim, deep red or infrared from the residual heat of its formation, a fading ember in the cosmic dark. Finding such an object orbiting alone in space is fascinating, but discovering one as a full-fledged, gravitationally bound member of a Quattuordecuple star system is a revelation that blurs every line we have drawn. Imagine a prestigious academy for brilliant scholars, a place where 14 prodigies live and work together. Now picture among them, accepted as an equal member, someone who audited the classes but never quite passed the final exam to earn the full title. That is the bizarre reality of a brown dwarf in this extreme family. Its presence forces a fundamental question about the system's formation. Did it form alongside the true stars, a smaller fragment from the same collapsing cloud that just fell short of the critical mass needed for fusion? Or does its existence point to a different, more hierarchical process? One compelling theory suggests that brown dwarfs in these systems are not failed stars at all, but overachieving planets. In the chaotic gravitational environment of the stellar nursery, the disk of material around a forming star could have been disrupted, causing large clumps of gas to break away and collapse directly into planetary mass objects. Some of these clumps might have been massive enough to become brown dwarfs, forming not like stars from a cloud, but like planets from a disk, yet ending up with enough mass to nearly cross the stellar threshold. Their existence within the Quattuordecuple family challenges the very definitions we use to categorize celestial bodies and suggests that the line between a very massive planet and a very small star is not just blurry, but may be meaningless in the context of such a dynamically rich birthplace. The quiet presence of a brown dwarf hints at a deeper, invisible struggle that shaped the entire family. Every spinning object in the universe possesses a property called angular momentum, a measure of its rotational inertia. Think of a figure skater pulling in her arms to spin faster, or a child on a merry-go-round holding tight. In the cosmic birth of a star system, this angular momentum is sacred. It must be conserved, neither created nor destroyed, only transferred or shared. When a giant cloud collapses to form stars, its initial slow spin accelerates dramatically as it shrinks, just like that skater. For a single star like our Sun, most of that spin ends up in the star's own rotation and the orbiting planets. But for a system of 14 suns, the accounting of this cosmic spin becomes a maddening puzzle. The 18th discovery is a profound imbalance in the ledger. When astronomers calculate the total angular momentum of certain Quattuordecuple systems, adding up the spin of each star on its axis, plus the orbital momentum of all their intricate dances, the numbers make no sense. Some systems have a net angular momentum far too low for their total mass. It is as if a massive, spinning cloud collapsed into this complex family, but most of the spin simply vanished. Where did it go? The leading suspect is a violent event that carried that momentum away, like a thief in the night. The prime candidate is the ejection of a runaway star. If the system once had 15 or 16 members, and one was violently flung out at tremendous speed, that escaping star would have taken a huge amount of angular momentum with it. The remaining 14 stars would be left in a strangely sedate state, their collective spin muted by the loss. The system's unnaturally low momentum is the ghostly signature of that missing sibling, a fossil record written not in rock, but in the silent mathematics of spin. Conversely, other systems show the opposite problem, an angular momentum that is suspiciously, impossibly high. How can a group of stars possess more spin than the cloud that birthed them could have possibly provided? This points to a different kind of cosmic theft, not a loss, but a capture. Perhaps this system did not form in isolation. As it drifted through a dense region of the galaxy, it might have had a grazing encounter with another star cluster or a massive, fast-moving interstellar gas cloud. In that gravitational interaction, the system could have stolen angular momentum, like a skilled billiard player adding spin to the cue ball. The passing object transferred some of its own motion, spinning up the entire Quattuordecuple family to a frenetic pace it was never born with. This creates a startling image of these systems not as closed, isolated islands, but as active participants in the galactic economy, trading the fundamental currency of motion with the wider cosmos. Both scenarios, the missing spin and the stolen spin, reveal a history far more dramatic than their current stable orbits suggest. The angular momentum ledger is a forensic tool, telling us that the serene dance we see today is the calm after a storm, or the prize won in a forgotten gravitational contest. The angular momentum of these families tells a story of theft or loss, a drama that often ends with the survivors drifting far from the scene of the crime. This leads to a 19th discovery that defies all intuition about where such cosmic families should live. We naturally assume that the most complex, crowded star systems must reside in the busiest stellar neighborhoods, the dense cores of glittering globular clusters, or the vibrant hearts of spiral arms where star birth is constant. In these crowded cities, gravitational encounters are frequent, providing both the raw material and the dynamic environment to build and sustain such intricate groups. Yet when astronomers finally pinpoint the galactic addresses of several Quattuordecuple systems, they found something profoundly unsettling. Many of them are not in dense clusters at all. They are isolated, drifting alone in the vast, quiet emptiness between the spiral arms, in regions astronomers call the galactic field. These 14 sun families are cosmic hermits, floating in profound solitude against the dark velvet of interstellar space. This isolation is baffling. It is like finding a bustling, thriving metropolis of 14 skyscrapers not on a continent, but adrift in the middle of the open ocean, with no land in sight. How did they get there? The formation of such a complex system requires an immense amount of gas and dust, and a crowded environment of stellar embryos. Those conditions simply do not exist in the lonely galactic field. So the inescapable conclusion is that these systems were not born in isolation. They were born in the dense, violent stellar nurseries we expect, but then something extraordinary happened. They were ejected, not just a single runaway star, but the entire family of 14 was violently kicked out of its birthplace as a single, intact unit. Picture a stellar nursery as a crowded party. Gravitational interactions are constant, like guests bumping into each other. Sometimes, a particularly strong shove sends one person stumbling out the door alone. That is a runaway star, but what we are seeing here is different. It is as if a tight-knit group of 14 friends, all holding onto each other, received a collective, perfectly coordinated push that sent the entire linked group flying out of the party and into the empty street outside without breaking their formation. The physics of this is staggering. For gravity to expel a bound system of 14 massive stars, it would require an encounter with something extraordinarily powerful, perhaps a close pass with a supermassive black hole at the cluster's core, or a catastrophic gravitational interaction with another massive star cluster. The energy required is almost unimaginable, yet the evidence suggests it happened. These isolated families are the refugees, their stable orbits a testament to their resilience. They survived a gravitational trauma that should have torn them apart, and now they travel the galactic hinterlands as a self-contained island universe. A reminder that even the most settled cosmic communities can be uprooted and sent wandering into the void. Their isolation makes them silent sentinels, but the space around them holds a memory of sound and fury. Light takes time to travel, and in the vastness around a Quattuordecuple system, it can become trapped in an echo. This is not a sound wave, but a literal echo of light itself. Imagine a single, brilliant flash, a supernova explosion, or a cataclysmic stellar flare erupting from one of the 14 suns centuries ago. That initial burst of light races outward in all directions at, of course, the speed of light. But space is not a perfect vacuum. It is filled with tenuous clouds of interstellar dust, microscopic grains of silicon and carbon floating in the dark. When the flash from that ancient explosion reaches a dust cloud, some of the light is absorbed, but a fraction is reflected, scattered in new directions. An observer, like our telescopes on Earth, sees the initial flash arrive first. Then, years or even centuries later, we see the reflected light finally reach us, having taken a longer, indirect path. This delayed glow is a light echo, a ghost of a violent event replaying itself on a cosmic stage. Around several of these 14 star families, astronomers have not found a single, simple echo. They have discovered something far more complex and haunting. Using deep field imaging that can detect the faintest glows, they have mapped intricate, nested shells of light echoing through the dust. Picture throwing a handful of pebbles into a still pond at different times. You would see multiple sets of expanding rings, each overlapping and interfering with the others. That is what surrounds these systems. The observations reveal not one, but several distinct shells of echoing light, each expanding outward at the speed of light from a different point in time. This nested structure is a forensic timeline of violence. The outermost, largest shell corresponds to the oldest event, perhaps a supernova that occurred 1,000 years ago. Inside it, a second, smaller shell tells of another catastrophe 500 years later. Within that, a third, even fainter ring speaks of a flare or eruption just a century past. These are not random cosmic fireworks. They are a chronicle written in reflected light, suggesting this family of suns has a cyclical history of self-destruction. The most likely culprit for the largest echoes is a supernova, the death of one of the original 14. This presents a staggering implication. If a star in this tightly bound group went supernova, the blast wave and the sudden loss of its mass would have delivered a gravitational hammer blow to the entire system. The remaining 13 stars would have been violently jolted, their orbits scrambled in an instant. The fact that we see a stable system today means it somehow survived this apocalypse and reorganized itself into a new, stable configuration, a testament to gravitational resilience that borders on the impossible. The smaller, more recent echoes likely point to a different kind of violence, perhaps titanic flares from the system's remaining massive stars, or from magnetic reconnection events in the tangled web that links them. Each echo is a chapter in an ongoing saga, revealing that the quiet harmony we perceive is a temporary peace in a war that has been raging for millennia. The light we see today from these stars is their present. The echoes are their past, still catching up to us, showing us a history of repeated stellar trauma that the system itself has endured and, against all odds, survived. The light echoes are a chronicle of stellar death, but the system's living members tell an even more vivid story. Discovery 21 reveals a single Quattuordecuple family that is less a nursery and more a stellar retirement home, a cosmic zoo containing nearly every stage of a star's life and death. Within the gravitational bounds of one ancient system, astronomers have identified a red giant, a white dwarf, several ordinary main sequence stars like our Sun, and the spinning corpse of a massive star, a pulsar. This is not a family of peers, but a snapshot of cosmic time, a collection of celestial generations living under one roof. The red giant is a star in its final, bloated act. Having exhausted the hydrogen fuel in its core, it has begun to burn helium, swelling to hundreds of times its original size, its outer layers cooling to a ruddy glow. It is a star in its old age, soon to shed its outer layers entirely, The white dwarf is what comes next. It is the exposed, ultra-dense core of a star that has already died, a stellar ember about the size of Earth, but containing nearly half the mass of our Sun. It is the ghost of a star that was, shining only with leftover heat, slowly fading into the dark. Among them burn the main sequence stars, still in the prime of life, steadily fusing hydrogen like our own Sun. And then there is the pulsar. This is the remains of a star far more massive than the others, a supernova's legacy. It is a neutron star, a city-sized sphere of pure nuclear matter so dense a teaspoonful would weigh 1 billion tons. Spinning rapidly, it beams out lighthouse-like pulses of radiation with metronomic precision. Its very presence is a declaration of past violence. Finding this entire menagerie together is profoundly strange. Stars of such different masses and ages should not coexist in a bound family for long. A massive star that becomes a pulsar does so in a supernova explosion of unimaginable power, an event that should have blasted its siblings away or completely disrupted their orbits. The fact that the white dwarf, the red giant, the pulsar, and the main sequence stars are all still here, still bound, means this system endured that cataclysm. It absorbed the titanic shockwave and the sudden loss of a huge fraction of its mass, and it held together. This resilience suggests a gravitational bond of almost incomprehensible strength, a family tie that not even stellar death could sever. This collection tells a complete story. We are seeing the past, present, and future of stars all at once. The main sequence stars are the present. The red giant is the near future for one of them. The white dwarf is the far future for another. And the pulsar is the dramatic, explosive past they all somehow survived. This system is not just a group of stars. It is a living museum of stellar evolution, a place where time itself has become tangled, showing us the entire life cycle of suns within the confines of a single, unbreakable gravitational embrace. The stellar museum of life and death is not silent. Its deepest movements are felt across the cosmos as ripples in spacetime itself. As we enter the era of gravitational wave astronomy, listening to the universe with instruments like LIGO and Virgo, a strange new kind of cosmic noise is emerging from the data. It is not the sharp chirp of colliding black holes or the steady thrum of merging neutron stars. It is a low, persistent hum, a background static woven from the motions of the most complex star systems in the galaxy. This is the gravitational foreground noise created by countless Quattuordecuple families. Every wobble, every shift in the intricate dance of 14 stars generates a minuscule ripple in the fabric of reality. A single system produces a signal far too faint and low frequency for our current observatories to detect. But multiply that signal by the estimated thousands of such systems scattered across the Milky Way, all contributing their own unique, ultra-slow gravitational wobble, and the combined effect becomes something measurable. It creates a constant, seething murmur underlying everything else, like the sound of a distant, bustling city heard from a quiet room. For astronomers, this is both a challenge and an opportunity. This gravitational hum is a form of pollution, a foreground noise that future, more sensitive observatories, like the planned LISA mission in space, will have to carefully identify and filter out. To hear the faintest whispers from the earliest universe, like the mergers of supermassive black holes at the dawn of time, they must first subtract this chorus of nearby stellar complexity. But in that noise lies a treasure map. By analyzing the specific frequencies and patterns within this gravitational background, scientists could, in theory, statistically infer the population of these extreme systems across the galaxy without ever seeing them directly. The hum becomes a census, telling us how many 14 star families exist, and perhaps even something about their average masses and separations. It is a reminder that the universe is not just a collection of isolated events, but a symphony of continuous motion, where even the most exotic families contribute their own note to the gravitational song of the Milky Way. This gravitational hum is the universe's most subtle music, but the true rhythm of life would be set by the light of its many suns. For any world that dared to form in such a place, the concept of a stable, life-giving orbit becomes a dizzying puzzle. Astronomers call it the habitable zone, that narrow band around a star where temperatures are just right for liquid water to exist on a planet's surface, a prerequisite for life as we know it. Around our single sun, this zone is a stable, donut-shaped region. In a Quattuordecuple system, this simple idea shatters into pure chaos. The habitable zone is not a place, it is a constantly moving target, a shimmering wave of possibility that washes through the system. A planet would not orbit a single star. It would orbit the system's shifting center of mass, a point constantly tugged between its 14 gravitational masters. As it travels along its own complex path, it would find itself bathed in the intense, blue-white glare of a massive star for a time, then later receiving only the faint, red warmth of a dwarf. The combined starlight from all 14 suns would create a background glow, but the primary source of heat would change dramatically over the course of a single long year. This means the planet's habitable zone moves with it, an invisible bubble of rightness that the world must somehow stay within. Climate on such a world would be beyond anything we can imagine. You could have seasons dictated not by axial tilt, but by which star or combination of stars is dominant in the sky. A period of decades under a gentle red sun could be a tranquil, prolonged summer, only to be violently interrupted as the planet's path swings it close to a blazing blue giant, triggering a sudden, scorching super summer that evaporates oceans and bakes continents in a matter of years. The sunsets would be a work of celestial art, with multiple suns of different colors and brightness dipping below the horizon in a staggered, ever-changing sequence. Yet, against all odds, astronomers have found planets in multi-star systems, including some with 3 or 4 suns. These worlds prove that planet formation can persist even in gravitational madness. The climates there, however, would be stranger than any science fiction. Computer models suggest such a planet might experience runaway greenhouse effects, followed by sudden global freezes, a climatic roller coaster driven by the changing stellar menu. Life, if it could arise at all, would need to be unimaginably resilient, perhaps hibernating deep underground or in ocean trenches for centuries during the hostile epochs, only to bloom in frantic, brilliant explosions during the rare, perfect alignments of stellar warmth. The discovery of these shifting habitable zones forces us to expand our definition of where life could exist, but it also reveals a universe where the conditions for life are not a steady state, but a fleeting, dancing coincidence in a storm of 14 suns. The shifting dance of 14 suns should leave a permanent haze in its wake. When massive objects orbit this close, collisions are inevitable. Asteroids, comets, and dwarf planets should be constantly shattering, grinding their remains into fine, warm dust that glows brightly in infrared light. This dust becomes a permanent fixture, a shimmering, heated shroud enveloping the entire stellar family. Yet when astronomers pointed the most powerful infrared telescopes at one particular Quattuordecuple system, they saw nothing. The expected brilliant glow of a massive debris disk was simply missing. The space between these 14 stars was suspiciously, unnervingly clean. This absence is a louder signal than any presence could be. It tells us something has recently and violently swept this system clean. The first suspect is a stellar wind of unimaginable force. Recall the lone, brilliant O-type star that sometimes dominates these families. Such a star does not just shine, it screams. It pours out a hurricane of charged particles, a stellar wind millions of times more powerful than our sun's solar wind. If this titan went through a period of extreme activity, or if the orbital dances brought all 14 stars into a configuration that focused their collective winds, the effect would be like using a cosmic leaf blower on the entire system. The combined force could have scoured every speck of dust, every tiny grain, right out of the gravitational grip of the stars, pushing it into interstellar space. The system would be left polished and empty, a silent testament to a cleansing gale that swept through perhaps just a few years ago. But there is a second, more unsettling possibility. What if the dust did not leave, but was consumed? In the chaotic gravitational tides, the orbits of dust grains would be highly unstable. Instead of being blown outward, much of the material could have spiraled inward, drawn down onto the surfaces of the stars themselves. This would be a slow, silent feast. The stars would have ingested the rocky remains of their own planetary systems, their atmospheres subtly enriched by the heavy elements of shattered worlds. This would leave no infrared glow, only a cryptic chemical signature in the starlight. The missing dust forces a stark choice between two narratives. Either this family of suns recently weathered a storm of its own making, a purifying blast that left it sterile, or it is a system still actively devouring its past, quietly absorbing the last evidence of the planets it failed to raise. The clean space between these stars is not empty. It is a crime scene where the dust has vanished, and the only clues are the silent, shining suspects themselves. The pristine emptiness between stars can hide the most violent of family secrets. Deep within the spectral fingerprints of one particular 14-sun family, astronomers have found the smoking gun of stellar cannibalism. The light from one of the member stars tells a story of consumption. Its atmosphere is contaminated with an overabundance of helium and heavy elements like lithium, a chemical signature that makes no sense for a star of its current size and temperature. This is the cosmic equivalent of finding undigested remains in a predator's stomach. The explanation is as brutal as it is elegant. This star was once part of a tight binary pair, orbiting a more massive companion. Over eons, as the more massive star aged and expanded into a red giant, its outer layers spilled over. The gravitational boundary between them, called the Roche lobe, was breached. The smaller star we see today began to violently siphon material directly from its bloated sibling, gorging itself on stellar plasma. This feast did not last forever. The transfer of mass and angular momentum caused the stars to spiral inward, culminating in a final, catastrophic merger. The larger star was completely consumed, its material mixed into the outer layers of the survivor. What we observe now is not the original star, but a stellar chimera, a reborn object shining with the combined fuel and the atmospheric ashes of its devoured twin. This single act of cannibalism would have sent a gravitational shockwave through the entire 14-body system. The sudden change in mass at the heart of that binary pair, and the release of energy from the merger, would have acted like a bomb going off in a precisely tuned clock. Every other star in the family would have felt a violent jolt, their delicate resonant orbits suddenly and severely perturbed. computer simulations suggest the system likely entered a period of profound chaos, lasting perhaps tens of thousands of years, with near misses, wildly changing orbits, and the very real risk of ejecting other members or triggering further collisions. The fact that the system today appears stable is a testament to its incredible gravitational resilience. It somehow found a new equilibrium, a fresh set of orbital dances that accommodated the new, more massive single star where a binary once existed. This means the harmony we observe is not the original score, but a revised composition, written in the aftermath of a stellar death and rebirth. The cannibal star now sits as a permanent monument to the system's violent past, its strange light a constant reminder that even in a family of 14, sometimes one sibling consumes another to survive. This act of stellar cannibalism reveals a deeper truth about the mathematics governing these families. Simulating the future of a Quattuordecuple star system is one of the most daunting challenges in all of computational astrophysics. It is known as the n-body problem, and for 14 suns, it becomes a nightmare of pure chaos. The task seems straightforward. You feed a supercomputer the current positions, velocities, and masses of all 14 stars. You program in the immutable law of gravity. You press start, and the machine calculates how each star pulls on the others, tracing their paths forward in time, year by year, for billions of simulated years. In reality, this process hits a wall almost immediately. The issue is not raw computing power, though that is immense. The issue is a fundamental property of chaos theory, often called the butterfly effect. In a system this complex, the gravitational influence of every single star matters, down to the most infinitesimal level. A change in the starting position of one star by a distance less than the width of an atom, or a variation in its speed by a fraction of a millimeter per second, will completely alter the entire simulation's outcome. Run 2 simulations with these imperceptibly different starting points, and for the first few million virtual years, they will look identical, but then the paths begin to diverge. After 10 million years, one star might be in a slightly different part of its orbit. After 50 million years, that tiny difference has cascaded through the entire web of gravitational relationships. In one simulation, 2 stars have a close encounter that ejects a third. In the other simulation, those same 2 stars never come close, and the system remains intact. By 100 million years, the 2 simulations bear no resemblance to each other. One might show a stable, resonant configuration, while the other depicts a violent disintegration. This extreme sensitivity means that no matter how precisely we measure these systems today, we can never know their exact future. Their long-term fate is fundamentally, mathematically unknowable. This is the discovery of chaotic stability. The systems we observe are clearly stable, having survived for millions or billions of real years. Yet our best tools tell us they should not be. The simulations suggest that stability in a 14-body system is not a permanent, solid state, like a rock. It is more like the delicate balance of a spinning top. It is stable for now, but a tiny, unmeasurable nudge could, in theory, send it tumbling into a new configuration. The fact that we see these systems at all means they have either avoided those nudges through sheer cosmic luck, or they possess a hidden, self-correcting mechanism that our crude simulations cannot yet capture. They exist in a state that is both stable and chaotic, predictable in the short term but utterly mysterious in the long term, a permanent question mark written in the motions of 14 suns. This mathematical chaos occasionally resolves into a form of breathtaking celestial geometry. Among the menagerie of 14 sun families, One configuration stands apart for its stark, almost artificial beauty. Astronomers have found a Quattuordecuple system where the stars are not tangled in a tight, spherical cluster, but are instead arranged in a nearly straight line, a gentle arc of 14 suns strung across the void like pearls on an invisible necklace. This string of pearls configuration is so visually striking, it seems to defy the very nature of gravitational systems, which tend to pull matter into blobs and disks, not perfect lines. The formation of such an elegant alignment presents a cosmic puzzle with two compelling solutions. The first theory reaches back to the system's birth in the cold, dark nurseries of interstellar space. Stars are not born from formless blobs alone, but often within vast, snaking structures called filaments. These are rivers of dense gas, light years long but only a fraction of that in width, weaving through the galaxy like the threads of a cosmic spiderweb. Within these filaments, gravity works section by section, causing beads of gas to condense at regular intervals. It is possible this entire 14-star family is the direct offspring of a single, incredibly massive filament. Each star formed at a separate knot or bead of density along that primordial thread. Instead of then collapsing into a messy cluster, the gravitational memory of that linear structure held, with the stars remaining roughly aligned along the ghostly spine of their birth filament. They are not in a straight line by accident, but by inheritance, a perfect fossil of the cloud that made them. A second, more dramatic theory suggests this beautiful line is not a birthmark, but a scar. Perhaps the system did form as a more traditional spherical cluster. Then, in its distant past, it had an extraordinarily close encounter with a truly massive object, something like an intermediate mass black hole or a dense, rogue star cluster passing through its neighborhood. The gravitational tide from this interloper would have been immense, acting not as a simple push, but as a stretching force. Imagine holding a clump of wet sand and slowly pulling it apart between your hands. The cluster of stars would have been tidally stretched, with the stars on the leading and trailing edges feeling the strongest pull. Over time, this could have drawn the entire family out into this long, elegant arc, a process called tidal filamentation. In this scenario, the pearls are not primordial, but were strung by a passing cosmic giant that reshaped the entire system in its wake, leaving behind this slender monument to a forgotten gravitational encounter. The string of pearls arrangement has profound consequences for the stars themselves. Their alignment means their gravitational influences are channeled along a single axis, creating a strange and focused dynamic. Stellar winds and radiation from one star blast more directly down the line onto its neighbors, potentially stripping atmospheres or influencing the magnetic fields of the next pearl in the chain. If any planets exist in this system, their night skies would be a spectacle of impossible geometry, with a procession of suns rising and setting in a near-perfect line across the heavens. This configuration stands as a quiet rebuke to our assumptions of cosmic disorder, proving that from the most chaotic gravitational laws, structures of serene and startling symmetry can emerge. The serene geometry of a string of pearls is a cosmic illusion, masking the true velocity at the heart of these families. In a typical multiple star system, orbital periods are measured in years, decades, or even centuries. A binary pair might take a few years to circle each other, while a distant tertiary companion could require a human lifetime to complete a single loop. This leisurely pace allows for stability, giving gravity ample time to maintain order. The 28th discovery shatters this expectation with a violence of motion. Within the core of certain Quattuordecuple systems, Astronomers have found pairs of stars that complete their entire mutual orbit not in years, but in a matter of days, or in the most extreme cases, mere weeks. This is not a gentle waltz, it is a frenetic, blurring spin. To complete a full circle so quickly, these stars must be orbiting so close together they are practically touching, separated by a distance often less than that between Mercury and our Sun. At such proximity, their orbital speeds are almost incomprehensible, reaching millions of miles per hour. These are not stars calmly sharing space. They are stellar engines locked in a death spiral embrace, whipping around each other at a significant fraction of the speed of light. The forces involved are apocalyptic. The gravitational tides between them are not the gentle, rhythmic pulls we associate with our moon, but continuous, crushing squeezes that actively reshape the stars into teardrop forms, stretching their atmospheres into shared bridges of superheated plasma. This constant, violent flexing generates immense internal friction, cooking the stars from the inside out with tidal heating far beyond anything we see in our solar system. The environment around such a pair is a perpetual storm of radiation and stellar wind, a maelstrom where the magnetic fields of the two stars are permanently tangled, likely triggering constant, colossal flares. The existence of such a rapid binary within a larger system of 14 is a gravitational tightrope act of staggering precision. The frantic dance of the inner pair must be perfectly balanced against the more stately pulls of the dozen other stars in the system. A slight misstep, an extra nudge from a passing sibling, could cause this already unstable duo to spiral even closer, hastening a merger or a catastrophic ejection. These ultra-fast orbits are a ticking clock, a signature of a system living on the very edge of dynamical possibility, where the music of the spheres is played at a dizzying, dangerous tempo. The frantic dance of 14 suns may be broadcasting its secrets across the cosmos in the most enigmatic code we have ever detected. These systems are now suspects in one of astronomy's greatest modern mysteries: fast radio bursts. An FRB is a pulse of radio waves of almost unimaginable power, often releasing more energy in a thousandth of a second than our sun does in an entire day. Most appear to come from distant galaxies, flaring once and vanishing forever, but a rare few are repeaters, sending out sporadic, powerful chirps from the same patch of sky. When astronomers meticulously trace the paths of these repeating signals back through the void, a curious pattern emerged. For several of them, the line of sight passes alarmingly close to the location of known Quattuordecuple star systems within our own Milky Way. This is not yet a confirmed link, but the coincidence is too tantalizing to ignore. It forces a staggering question. Could the extreme physics within a family of 14 stars be the engine for these cosmic sirens? The conditions there are uniquely suited for catastrophe. Imagine the tangled magnetic web connecting these suns. When stars in their complex dance swing close, their magnetic fields can snap and reconnect in a violent process that accelerates particles to nearly the speed of light. This could generate a focused beam of radio energy so intense it briefly outshines entire galaxies. Another possibility involves the cannibal stars or the neutron star pulsars that sometimes reside in these families. A sudden avalanche of material onto a pulsar's surface, or a starquake on its impossibly dense crust, could release a blast of energy that travels perfectly through the clean, dust-scoured space between the stars, reaching us as a sharp, clear burst. These systems are natural particle accelerators and gravitational pressure cookers, places where energy builds and releases in sudden, violent acts. If the connection is real, then each mysterious radio chirp is not just a random blast, but a distress call or a triumphant shout from the most complex gravitational relationships in the universe. A fleeting signal from a dance we are only beginning to understand. The sky above a world with 14 suns would be a canvas of shifting, impossible colors. This is not a single, steady blue or a constant deep black, but a living palette that changes with the complex orbital clockwork of its stellar family. Astronomers can now reconstruct these alien skyscapes, not with artists' brushes, but through the precise mathematics of light. By analyzing the combined light curve of the entire system, that chaotic graph of flickering brightness, and breaking it down into the individual spectral signatures of each star, they can calculate which stars are above the horizon of a hypothetical planet at any given moment, and in what combination. The result is a color forecast for an alien world. For a period, the planet might orbit in the gentle glow of two cool red dwarf stars. The sky would be bathed in a perpetual, dim twilight of deep crimson and burnt orange, casting long, soft shadows. Vegetation, if it existed, might evolve to be black to absorb every precious photon of this faint red light. Then, as the planet's path continues, a brilliant blue-white O-type giant swings into view, rising alongside the red dwarfs. The sky's color would violently shift. The dominant blue-white light would bleach the reds, creating a harsh, metallic lavender or a searing, pale silver. The contrast would be blinding, the shadows sharp and short. This is not a sunset. It is an entire atmospheric recalibration. The most profound moments come during complex conjunctions, when 3, 4, or 5 stars of different spectral classes cluster in the sky. Their light mixes not like paint, but like overlapping spotlights in a theater. The human eye would struggle to process it, potentially seeing a muted, pearlescent gray, while the true spectral reality is a riot of unmixed colors. Scientists have coined a term for this: chromatic seasons. A world might experience a crimson epoch under a dominance of red dwarfs, followed by a cerulean age when blue giants rule the heavens, each lasting for decades or centuries. The light itself would have a strange, tangible quality, lacking the pure, directional source of a single sun. Shadows would be multiple, faint, and confusing, cast in different directions by different suns, sometimes canceling each other out to create a diffuse, shadowless glow. The very concept of day and night dissolves. True darkness might only come during a rare and perfect alignment, when the planet slips into the collective shadow of several stars. A brief, deep night that could be the most precious and terrifying event on that world's calendar. This reconstructed sky is more than a visualization. It is a fundamental constraint on life. Photosynthesis would need to be spectacularly adaptable, able to switch its chemical pathways to harness energy from red, yellow, or blue light as the chromatic seasons turn. Animal vision would evolve to prioritize contrast in a world of confusing, multi-hued shadows, or perhaps to see in a much broader spectrum than our own. The color-changing sky is the ultimate expression of the system's chaos and harmony, a daily reminder to any potential inhabitants that they live under the rule not of one sun, but of a constantly changing committee of 14. The color of an alien sky is written in the chemistry of its suns, a permanent record of ancient violence. Within the atmospheres of certain stars in these 14 sun families, astronomers have found a cryptic, glittering signature. Their light reveals an astonishing overabundance of the heaviest, rarest elements in the universe: gold, platinum, and uranium. These metals are not forged in the quiet furnaces of ordinary stars. They are the product of the most catastrophic explosions imaginable, events called hypernova. A hypernova is a supernova's terrifying big brother. It is the death scream of a star so massive, so unstable, that its core collapse does not produce a mere neutron star, but triggers a runaway chain reaction that rips the star apart with almost inconceivable force. The energy released can briefly outshine an entire galaxy, and in that apocalyptic fury, atomic nuclei are bombarded with such intensity that they fuse into the heaviest elements known. These precious, dense metals are then blasted into the surrounding cosmos at nearly the speed of light, a glittering shrapnel of cosmic creation. The discovery here is that several stars in a single Quattuordecuple system share this same specific metallic fingerprint. They all possess this unexpected wealth of gold and platinum. This is not a coincidence. It is a family trait, but one that was not inherited at birth. The primordial cloud that birthed these 14 suns would have contained only the basic elements: hydrogen, helium, and traces of lithium. For all 14 siblings to now be enriched with the same rare, heavy metals means they were all polluted by the same event after they had already formed. The scenario is both breathtaking and terrifying. Early in this system's life, perhaps just a few million years after the stars ignited, a neighboring star, a true cosmic titan living just a few light years away, reached the end of its life. It did not go quietly. It erupted as a hypernova. The blast wave, carrying its cargo of newly forged gold and platinum, would have swept through the Quattuordecuple system like a tidal wave of cosmic dust. The stellar winds of the 14 suns were no defense. For centuries, the sky within the system would have glittered with the incoming debris, as trillions of tons of precious metals rained down on the stars, settling into their outer atmospheres and forever altering their chemical composition. This event would have been more than a light show. It was a gravitational and radiative catastrophe. The sheer force of the blast wave likely compressed the gas between the stars, triggering new rounds of star formation or violently perturbing their orbits. The system we see today had to survive not only its own internal chaos, but also this external, galaxy-shaking hammer blow from a dying neighbor. The gold in their light is more than an element. It is a scar, a permanent memorial to a day, millions of years ago, when a nearby sun died in a blaze of glory so profound it literally gilded an entire family of stars, leaving them forever touched by the most violent alchemy in the universe. The golden scar of a hypernova is a mark of what the system has endured, but it also hints at a more active, predatory nature. These massive families do not just survive external violence, they can initiate it, acting as gravitational predators in the cosmic dark. Dynamical studies reveal a startling behavior. A massive Quattuordecuple system can function as a trap, a deep well in the fabric of space-time that slowly ensnares passing stars. Picture a dense, ancient forest. A massive, complex bramble bush sits at its center, a tangled structure with immense gravitational pull. A solitary animal, or even a pair, wandering too close might become caught, its path irrevocably altered as thorns and vines gently but firmly pull it into the heart of the thicket. In cosmic terms, the bramble bush is the 14-star system, its gravity the thorns. The wandering animals are single stars or binary pairs drifting through the galactic field. As one of these lone stars passes within the system's expansive gravitational influence, it doesn't simply sail by. The combined pull of 14 suns acts as a brake, subtly sapping its orbital energy. With each subsequent pass and over millions of years, there can be many, the star loses a little more speed, its path bending closer and closer to the chaotic core. Eventually, it crosses a threshold. It is no longer a visitor on a hyperbolic orbit, but a captive, its motion now bound to the intricate dance of the family. This process is not a quick, dramatic capture, but a slow, inexorable seduction by gravity. The system grows not from within, but by adoption, adding a 15th, then perhaps a 16th member to its already staggering roster. Astronomers have dubbed this behavior the stellar octopus model. The Quattuordecuple system is the central body, and its long, far-reaching gravitational tendrils are the arms, constantly feeling the space around it, ready to grasp and pull in any suitable mass that drifts within reach. This changes our understanding of these systems from closed, isolated islands to open, growing entities. A system we identify as having 14 members today might have had only 12 100 million years ago, and might harbor 16 100 million years from now. This gravitational cannibalism raises a profound question about stability. How does adding a new massive object not tear the delicate resonant web apart? The answer lies in the slow, gentle nature of the capture. The new star is not violently thrown into the mix. It is coaxed in, its energy dissipated over eons until it naturally settles into an available stable orbit, often a distant, hierarchical one that minimally disrupts the inner chaos. The system's existing complexity may even facilitate this, with gravitational resonances creating stable parking spots, Lagrangian points, that are waiting to be filled. This discovery means the 14-star system is not a finished product, but a living, growing gravitational ecosystem, forever changing its own composition by drawing in the lonely wanderers of the galactic night. This gravitational growth through capture should lead to orbital chaos, a tangle of paths tilted at every conceivable angle. Yet the universe has crafted a masterpiece of cosmic flatness. Astronomers have found a Quattuordecuple system where all 14 stellar orbits share the same precise plane, a single vast disk of motion thinner than a sheet of paper scaled to the size of the solar system. It is a giant, flat clockwork, a celestial phonograph record spinning in the void, with each star tracing its groove. This extreme coplanarity is a state of frozen geometry, defying the natural tendency for orbits to warp and precess under mutual gravitational nudges. In most complex systems, even triple stars, the orbital planes slowly tilt over billions of years, like a wobbly table gradually losing its balance. Here, that process has been arrested. The 14 orbits are locked in perfect alignment, a condition so pristine it could only originate from a single monumental event: formation from a stable, gargantuan protostellar disk. Picture the birth of our solar system. All the planets orbit in roughly the same plane because they formed from a flat, spinning disk of gas and dust around the infant sun. Now scale that idea up to a staggering degree. Instead of a disk that forms pebbles, then planets, this was a disk so massive, so laden with material, that its gravitational instabilities collapsed directly into stars. Each of the 14 suns is a direct child of that one primordial structure, condensing at different distances from the center like beads on a spinning wire. They inherited their flawless flatness from the geometry of their nursery, and the system's own internal gravity has vigilantly preserved that alignment ever since. This frozen architecture has profound consequences. It minimizes the chances of catastrophic close encounters, as the stars are all effectively running on separate, well-defined tracks on the same racetrack. It also suggests a birth environment of astonishing calm, to prevent the disk from warping or tearing apart during the tumultuous process of fragmenting into 14 separate stars. The surrounding region must have been exceptionally quiet, free from the gravitational bullying of passing star clusters or massive gas clouds. This system is not a product of chaos, but of a rare and prolonged cosmic serenity, a place where a single, perfect idea, a spinning disk, was allowed to execute itself with flawless precision, resulting in a family of 14 sons forever bound by the flat geometry of their origin. This pristine, flat geometry creates a deceptive calm, a stage perfectly set for cosmic predation. Within the orderly disk of one 14-star family, astronomers have spotted stellar vampires. These are blue stragglers, stars that burn with a deceptive, youthful blue intensity, standing out starkly among their older, cooler siblings. A blue straggler is a cosmic paradox, a star that appears younger than it should be. In a system where all stars were born together, they should all be aging at roughly the same rate, with the most massive ones burning out first. A blue straggler breaks this rule. It shines hotter and brighter, as if it had just ignited, while stars of similar mass around it have already faded toward their red giant phase. The secret to its stolen youth is not a fountain of cosmic vitality, but a literal fountain of stellar plasma siphoned from a neighbor. This is stellar vampirism. In a close binary pair, one star can expand in its old age, its outer layers becoming gravitationally vulnerable. Its companion, the vampire, then begins to siphon off this hydrogen-rich fuel, funneling it onto its own surface. This fresh fuel reignites the vampire's fusion processes with renewed vigor, making it hotter, bluer, and more luminous. It is effectively rejuvenated by consuming its companion. The donor star is left diminished, often stripped down to its helium core, a spectral ghost of its former self. In a typical star cluster, finding one or two such blue stragglers is notable. But within this particular Quattuordecuple system, astronomers have identified not one, but several of these brilliant blue anomalies, multiple stellar vampires, all glowing with stolen life, within a single family of 14. This is not a coincidence. It is a direct consequence of the system's extreme density and complex orbital choreography. The close quarters and frequent gravitational encounters within the 14-star disk create perfect conditions for vampirism. Binary pairs are nudged into tighter orbits, their mutual gravitational grasp tightening until one star's atmosphere spills over the cosmic dam. The intricate resonances that stabilize the system as a whole may also periodically drive stars into these intimate, predatory dances. The presence of multiple blue stragglers paints a picture of a system with a long and rampant history of mass transfer. It suggests epochs where the serene disk was a scene of silent, slow-motion feasting, with streams of superheated gas flowing between stars like celestial blood. Each brilliant blue straggler we see is a monument to a completed act of consumption, a star that extended its life by cannibalizing its partner. But this vampirism has a gravitational cost. The transfer of mass changes the balance of the binary pair, altering its orbit and, by extension, its gravitational influence on the other 12 stars. Each vampiric event is a tiny shock to the system's delicate clockwork, a perturbation that the grand resonance must absorb and accommodate. This means the flawless flatness of the disk, the very symbol of its ordered birth, has been maintained despite these repeated, violent acts of theft happening within it. The system's stability is not pristine, but rugged, having weathered not just external hypernova, but internal acts of stellar parasitism. These blue stragglers are more than oddities. They are evidence that even in a state of profound geometric order, the universe permits a savage, intimate struggle for survival, where one star's youth is purchased with the slow consumption of another. The silent predation of stellar vampires leaves invisible scars, but gravity itself can sometimes reveal them in the most unexpected ways. The universe has a trick for exposing hidden mass, a natural magnifying glass called gravitational microlensing. It works on a principle from Einstein's general relativity. A massive object, like a star or a black hole, warps the space around it. When this object passes almost perfectly in front of a much more distant star, from our viewpoint, that warped space acts like a lens. It bends and focuses the light from the background star, causing it to temporarily brighten, often by hundreds of times, before fading back to normal as the alignment passes. It is a fleeting cosmic flash, a chance alignment that lets us weigh the invisible foreground object. Normally, this produces a single, smooth peak in the light curve, a clean, symmetric bell curve. But when the foreground object is not a single star, but a Quattuordecuple system, the simple lens becomes a kaleidoscope. Astronomers witnessed this exact event. A 14-star family drifted, from our perspective, into the line of sight of a faraway star in the galactic bulge. What happened next was a light show of unprecedented complexity. Instead of one smooth brightening, the background star's light flickered and danced, erupting into not one, but several distinct peaks of magnification, each with its own strange shape and timing. The gravitational field of the 14 suns was so complex, so lumpy with mass, that it created multiple overlapping lenses within lenses. Imagine holding a handful of differently shaped glass beads over a single light source. The light would project a chaotic, shifting pattern of bright spots and dark bands on the wall. That is what the telescope recorded. Each star in the foreground system contributed its own tiny warp. Their combined gravity created a network of intersecting caustics, regions of extreme magnification. As the system moved, the background star's light rays traversed this warped landscape, brightening violently as they crossed a caustic, then dimming, then brightening again as they hit another. The resulting light curve looked less like a bell and more like the jagged readout of a seismograph during a major earthquake. This chaotic flickering was a treasure trove. By meticulously modeling this insane pattern, astronomers could perform a feat of cosmic tomography. They could map the mass distribution of the entire 14-star system without ever resolving the individual stars. The timing and height of each peak revealed the approximate masses and positions of the dominant gravitational players. It even hinted at the presence of otherwise invisible components, perhaps a faint brown dwarf, a swarm of planets, or a cloud of dark matter, whose gravity contributed a subtle extra warp to the lens. This single, chance alignment provided a snapshot of the system's entire gravitational skeleton, proving that its immense mass was not smoothly distributed, but clumped into 14 distinct knots of stellar power, their intricate dance frozen for a moment in the magnified light of a distant sun. The gravitational lens revealed a skeleton of mass, but the true violence of these families is written in a far more energetic light. X-rays pierce through cosmic dust, revealing the universe's most extreme environments, the million-degree coronae of stars, the searing disks of matter spiraling into black holes, and the shocked gas of colliding stellar winds. When astronomers pointed X-ray telescopes at one particular Quattuordecuple system, they expected a faint, diffuse glow, the combined murmur of 14 separate stellar atmospheres. What they detected instead was a searing beacon, an X-ray output so intense it outshone the combined visible light of all 14 suns. This was not a gentle hum, it was a scream. The energy required to produce such a torrent of high-energy photons defies any simple explanation. It suggests the system is not just a collection of stars, but a colossal engine of particle acceleration. One possibility is a shared, superheated atmosphere. If the stars are close enough, their individual million-degree coronae, the thin, outermost layers of their atmospheres, might be colliding and merging. Where these magnetized plasmas smash together at thousands of miles per second, they create shock waves that can accelerate electrons to near light speeds. As these frenetic particles spiral along tangled magnetic field lines, they emit the intense X-rays we see. The entire volume of space within the system could be filled with this roiling, superheated soup, a single, connected halo of fury that engulfs all 14 members. An even more violent explanation points to accretion. Hidden within the stellar crowd could be a neutron star or a stellar mass black hole, a remnant from a past supernova. If this compact object is in a tight orbit with a normal star, it can voraciously strip material from its companion. That stolen gas doesn't fall in quietly. It forms a whirling, friction-heated disk around the invisible predator, a structure so hot it glows fiercely in X-rays before the material vanishes past the event horizon. The presence of such an object would be a ghost in the machine, an invisible gravitational anchor whose appetite lights up the system. Finally, the sheer chaos of the orbits themselves could be the power source. When two of the 14 stars, each with a powerful stellar wind, swing close in their dance, those supersonic outflows collide head-on. The collision zone becomes a natural particle accelerator, a permanent site of cosmic violence where temperatures soar to tens of millions of degrees, forging X-rays in a continual, raging storm. This unexpected brightness is a direct measurement of the system's inner turmoil, a gauge showing that the serene dance of suns is, in reality, a continuous series of high-energy collisions and consumptions, hidden from our eyes but blazing forth in the penetrating light of X-rays. The X-ray scream of these systems is a direct signal from the present, but their truest value lies in the ancient past they have perfectly preserved. Each of these 14 star families, especially the oldest among them, is a time capsule of galactic history, a field of study known as galactic archaeology. While we can study the galaxy's present structure and make models of its past, we lack a time machine to visit its formative eons. These Quattuordecuple systems are the next best thing. They are cosmic fossils, and their every property is a clue etched in stellar fire. To understand how, think of a single ancient tree deep in an old-growth forest. By examining its rings, a scientist can deduce the climate conditions of each year of its life, years of drought, seasons of abundant rain, even the scars of long-ago fires. A Quattuordecuple system is that tree, but its rings are the precise motions and chemical compositions of its 14 member stars. These stars were born together from the same cloud of primordial gas over 10 billion years ago, likely before the Milky Way's majestic spiral arms had even fully settled into their current form. At that moment of their ignition, they were imprinted with two indelible records. The first is a kinematic fingerprint, a precise record of how they were moving. The cloud from which they collapsed was itself moving through the early, chaotic galaxy, tumbling and spinning under the influence of the first giant structures. That inherited motion is still with them today. By measuring the exact, three-dimensional velocities of all 14 stars in one of these ancient families, astronomers can work backwards. They can subtract the gentle gravitational influences the stars have on each other. and what remains is their original systemic motion through space, the velocity vector they were born with. This tells us how the primordial gas cloud itself was moving. Was it part of a turbulent, chaotic flow, or was it already on a settled, circular orbit around the galactic center? This single data point from one system helps map the gravitational forces and the dynamic state of the infant Milky Way. The second, even more profound record is chemical. The cloud that formed these stars was a specific mix of elements. It contained the pristine hydrogen and helium from the Big Bang, but also traces of heavier elements carbon, oxygen, iron, that had been forged inside the first generation of stars and scattered by their supernova deaths. The exact ratios of these elements are a unique signature of that cloud's location and history. A cloud enriched by many early supernovae will have one chemical pattern. A cloud that formed from more isolated, pristine gas will have another. Because all 14 stars formed from that same cloud, they all share that identical chemical fingerprint, a recipe frozen in time. This allows astronomers to perform a kind of stellar genealogy. They can compare the chemical signature of an ancient Quattuordecuple system to those of other old stars and star clusters across the Milky Way. If they find a match, it means those seemingly separate groups share a common birthplace. They are long-lost siblings, all born in the same giant molecular cloud complex that was later torn apart by the galaxy's rotation. By connecting these familial links, astronomers can begin to reconstruct the architecture of the galaxy's earliest building blocks, the dwarf galaxies and massive clusters that merged to build the Milky Way we see today. Furthermore, the very existence of such a complex, bound system from that era tells a story about the early galactic environment. For 14 stars to form together and remain bound for over 10 billion years, their birth cloud must have been incredibly dense and their local neighborhood relatively quiet, free from the gravitational shocks that would have torn them apart. This suggests that some pockets of the early galaxy were not just chaotic firestorms, but had regions of surprising calm and immense density where gravity could work its most intricate magic. So, when we look at one of these ancient 14 sun families, we are not just looking at stars. We are reading a fossilized diary entry from the galaxy's childhood. Their motions tell us about the gravitational tides of a younger Milky Way. Their chemistry tells us about the life and death of the very first stars. Their mere survival tells us about the conditions in which the galaxy's first complex structures were forged. They are not merely inhabitants of the galaxy. They are living artifacts of its creation, holding secrets in their light that no telescope pointed at the present sky could ever reveal. The galaxy's most ancient families sometimes live alongside their own ghosts. Among the 14 suns of one particular system, astronomers have found a macabre gathering they call the Dance of the Dead. Here, the vibrant light of living stars is shared with the silent, dark remnants of those that have already died. Several members of this family are stellar corpses, white dwarfs, neutron stars, and likely stellar mass black holes, all still locked in the intricate gravitational waltz with their surviving siblings. This creates a graveyard orbit, a cosmic necropolis where the living and the dead continue their eternal dance. Imagine a grand ballroom where some dancers are glowing with life, while others are invisible, their presence only felt by the subtle, unnerving tug on their partner's hands. This system is that ballroom, a unique laboratory for studying the ultimate fate of stars in the most extreme environment imaginable. The white dwarfs are the quiet ghosts. These are the exposed, Earth-sized cores of stars that have gently shed their outer layers. leaving behind a dense, fading ember of carbon and oxygen. They emit no new energy, shining only with leftover heat. Yet in this crowded system, they are not inert. Their immense density gives them a gravitational pull disproportionate to their tiny size. As they swing through the complex choreography, they subtly warp the paths of the living stars around them. Their invisible weight, a constant reminder of a completed life cycle. More dramatic are the neutron stars. These are the pulsars, the rapidly spinning, city-sized remnants of massive stars that died in supernova explosions. Their presence is the system's most shocking fact. A supernova is a titanic blast that should have blown the entire family apart, ejecting stars and scattering orbits to the cosmic winds. The fact that a neutron star remains here, still bound, means the system somehow survived that stellar detonation. It absorbed the unimaginable shockwave and the sudden loss of a huge fraction of its mass, and it held together. The pulsar's metronomic radio ticks are now a precise clock embedded in the chaos, its regular pulses slightly altered by the gravitational pull of its 13 companions, allowing scientists to map the system's mass with incredible accuracy. Then there are the true voids, the suspected stellar mass black holes. These are the darkest partners in the dance. They reveal themselves only through their gravitational malice. Astronomers infer their presence by watching the living stars. One star might trace a wobbling, elliptical path that makes no sense unless an invisible object several times, the mass of the sun, is pulling on it. Another might show signs of being stretched by tidal forces, its atmosphere subtly siphoned away by an unseen companion. These black holes are the ultimate gravitational anchors, silent predators that continue to shape the lives of their stellar family long after their own light has vanished. This graveyard orbit transforms our understanding of stellar death. In the solitude of deep space, a star dies alone, its remnants drifting into the dark. But here, in a family of 14, death is a communal event with lasting consequences. The transformation of a star into a corpse changes the gravitational balance of the entire system in an instant. The loss of mass from a supernova causes every other star's orbit to suddenly expand or become more eccentric. The birth of a dense neutron star or black hole creates a new, intense gravitational point that the surviving stars must now dance around. This system shows us how a family of suns adapts to mortality. It demonstrates that gravitational bonds can be so strong they persist not just through life, but through catastrophic death and rebirth into a new, darker form. The dance of the dead is not a morbid end, but a new phase of existence, proving that in the cosmos, even the departed remain part of the family, their silent gravity forever a thread in the tapestry of motion. The very act of naming these systems reveals a hidden layer of their strangeness. Across the world, astronomers maintain vast digital catalogs, libraries of the cosmos where every star and galaxy is assigned a precise, if often dry, identifier. A solitary star might get a simple catalog number, while a tidy binary earns a designation noting its two components. The system is built for order, designed to bring the chaos of the universe into neat, searchable rows of data. But when a Quattuordecuple system is discovered, this entire bureaucratic machinery of the stars grinds to a halt. The discovery is that these families of 14 suns are fundamentally unclassifiable within our existing schemes. They do not fit. The result is a kind of cosmic comedy etched into scientific databases. Where you might expect a clean label, you instead find a sprawling, nearly unreadable string of letters, numbers, and nested parentheses that looks more like a corrupted line of computer code than a name. An entry might read something like a BCABDEFGHIJKLMN, where capital letters denote individual stars, lowercase letters indicate type binaries within the group, and the sheer length of the string is a frantic attempt to map the Byzantine relationships. Some catalogs resort to simply calling the whole thing by one primary star's name, and then adding a footnote longer than the original entry, a digital shrug from the astronomers who had to file it. This is more than an administrative headache. It is a profound insight. That convoluted catalog entry is a direct translation of the system's gravitational reality into human language. Each nested parenthesis represents a hierarchical level that may or may not actually be stable. Each letter tied to another reflects an orbital bond that is constantly being negotiated by 12 other suns. The classification struggles because our language for orbits is built for simplicity binary, triple, quadruple assuming clean, nested levels. The Quattuordecuple system laughs at these categories, presenting a reality that is a network, not a tree diagram. Trying to force it into a drop-down menu in an astronomical database is like trying to describe the entire internet structure with a single street address. The humorous, frustrating result is a testament to their complexity, a quiet admission that our tools for understanding the universe are still being outwitted by its creativity. Every time an astronomer has to invent a new, ridiculous string of characters to label one of these systems, they are not just doing paperwork. They are writing a tiny epitaph for simplicity, acknowledging that they have found something so richly woven it defies every box we have ever built to contain the stars. The catalog's tangled name is a confession of chaos, but that chaos may have a single, violent origin story. The great ejection theory offers a dramatic answer to the deepest question of all: why 14? Why not 12 or 16 or 20? Advanced computer simulations now suggest that the number 14 is not a starting point, but a finishing line. These systems we see today are not the original family, but the traumatized survivors of a stellar civil war. According to this model, a Quattuordecuple system begins its life not as a family of 14, but as a sprawling, chaotic mini-cluster of 20, 30, or even more newborn stars, all born together in an incredibly dense pocket of a stellar nursery. This infant cluster is a gravitational powder keg. For a few million years, it churns in a state of wild instability, a cosmic mosh pit where young stars are constantly nudging, pulling, and slingshotting past each other. In this environment, close encounters are not rare events. They are the norm, and with each gravitational grapple, energy is transferred. The simulations show a clear, brutal pattern. Through a series of these encounters, the stars begin to sort themselves. The slow, the unlucky, or those in unfortunate configurations have their orbital energy systematically drained. They sink deeper into the cluster's gravitational well, binding themselves tighter to the emerging core. Others, however, get a gravitational kick, a boost of velocity that sends them flying outward. This is not a gentle expulsion. It is a violent purging. Over a relatively short period, perhaps a few 100,000 years, the cluster experiences a phase of dynamical relaxation so intense it ejects nearly half of its original members. These runaway stars are flung into the galactic darkness, becoming solitary wanderers or joining other groups. What remains is not the original chaotic swarm, but a hardened, dense core of the most gravitationally committed stars, the ones whose motions and masses somehow found a mutual balance through all that violence. That surviving core, according to the mathematics, often stabilizes at a number remarkably close to 14. The theory paints these Quattuordecuple systems not as delicate creations, but as the last ones standing. They are the victors of a gravitational elimination round, a group that achieved a precarious ceasefire only after ejecting the members whose presence guaranteed perpetual war. The strange orbital architectures we see, the non-hierarchical dances, the twisted resonances are not birth patterns, but scars. They are the final, stable configuration that emerged from the storm, the only arrangement that allowed these particular 14 stars to stop ejecting each other. This means the serene dance we observe today is the quiet aftermath of a forgotten stellar exodus, a piece bought with the violent exile of its own siblings. Gravity's ruthless elimination left behind a stable core, but its creative work was far from finished. Within the cleared spaces between the 14 suns, a new and stranger form of construction began. The chaotic tides that had ejected stars and shattered worlds could also, paradoxically, become architects. This leads to a discovery that redefines what a planet can be. In the calm gravitational pockets that exist within the storm, vast clouds of dust and debris, the pulverized remains of those shattered worlds, did not simply disperse. Instead, the combined gravity of all 14 stars began to shepherd them. Over eons, this debris was not pulled into orbit around any single star. How could it be? The gravitational allegiance in such a place is constantly contested. Instead, the dust and rock coalesced into stable orbits around the system's center of mass, that invisible, shifting point in space that all 14 suns themselves dance around. These are not circumstellar objects like planets in our solar system. They are circumsystem objects. They orbit a ghost. Imagine a giant, invisible merry-go-round at the heart of the system. The 14 stars are like riders sitting at different distances from the center, some close, some far, all spinning. Now picture a child's toy car placed not near any rider, but directly on the empty central platform itself, circling the central pole. That toy car is a pseudo-planet. Its primary gravitational master is not a star, but the abstract mathematical point that represents the average position of all the stars' combined mass. These objects would be true children of the system itself, belonging to no single sun but to the entire gravitational family. In appearance, they might be vast, dark worlds of rubble, or perhaps gas giants that formed from the coalescing debris. Their skies would be a panorama of madness, with 14 suns of varying brightness whirling in complex patterns, never setting, only shifting positions in a perpetual, multi-hued day. Their years would be dictated by their loop around that empty center, and their climates would be bathed in the ever-changing blend of light and heat from all their stellar parents. These pseudo-planets are the ultimate testament to the system's emergent order, proving that even from the most violent chaos, gravity can carve out stable niches and build new worlds around the very idea of balance. This profound silence in the data speaks volumes. While we search the cosmos for whispers of intelligence, for the structured radio signals we call technosignatures, the 14 sun families offer only a blank reply. Astronomers have meticulously aimed the most sensitive radio telescopes at these systems, scanning the frequencies where a technological civilization might logically broadcast, listening for a pattern that stands out against the natural crackle of the universe. The result is not a mysterious signal, but the absence of one, a curious and profound nothing. In the place where we might hope to hear a deliberate hello, there is only the relentless hiss of cosmic noise, the static of stellar winds, and the chaotic chorus of 14 magnetically active suns. This radio silence is a discovery in itself, a piece of data that forces two deeply unsettling possibilities. The first is that the environment is simply too hostile. The shifting habitable zones, the climatic roller coasters, the X-ray bombardment, and the gravitational mayhem may present a barrier too great for complex life to ever arise or persist long enough to look to the stars. A civilization might bloom during a rare, stable alignment of stellar warmth, only to be sterilized when its world swings too close to a blue giant or is bathed in radiation from a magnetic reconnection event. Their window for technological development could be tragically short, closing before they ever learn to build a radio transmitter. The second possibility is far more intriguing and challenges our assumptions at a fundamental level. We are searching for signs that look like us, for a civilization that uses radio waves in a way we would recognize. But what if a society that evolved under 14 suns perceives and communicates with the universe in a way we cannot yet conceive? Their technology might be based on manipulating the complex gravitational fields themselves, or using the system's tangled magnetic web as a natural transmitter. Their signals might be embedded in the subtle orbital timing variations of the stars, a code written not in radio waves, but in the precise delays of eclipses. Or, facing a sky ablaze with lethal radiation, they might have abandoned wasteful broadcast methods entirely, using tightly focused laser pulses or neutrino streams for communication, signals that our current searches are blind to. Their entire concept of astronomy and signaling would be built around navigating and utilizing an environment of 14 gravitational masters, a physics so alien that their technological fingerprints might be invisible to our singular sun perspective. This radio silence, therefore, is not necessarily an empty answer. It is a mirror reflecting the limits of our own imagination. We are listening for an echo of ourselves in a place where the very definition of a self might be something entirely different. That profound radio silence is not a void of energy, but a blanket of warmth. Infrared telescopes reveal a startling fact about the space between these 14 suns. It glows. The immediate volume of a Quattuordecuple system is not the bitter, near absolute zero cold of interstellar space. It holds a persistent, gentle heat, a background temperature measurably higher than the dark, silent medium that surrounds it. This is not the intense blaze of a star, but a diffuse, all-encompassing warmth, as if the entire system is wrapped in a thin, cosmic blanket. This warmth defies the simple expectation that empty space between stars should be cold. The heat comes from a captive atmosphere, a ghostly shroud held in place by the system's collective gravity. Picture the combined light and stellar wind from 14 active suns. That torrent of energy doesn't just stream out into the galaxy unopposed. It encounters a tenuous, almost invisible fog of dust and gas, the last remnants of the primordial birth cloud, the fine debris from shattered asteroids, the slowly expelled material from stellar winds. This fog is too sparse to see with optical telescopes, but it is dense enough to matter. The system's gravity, that intricate web woven by 14 massive objects, is strong enough to hold onto this material. It cannot escape, so it hangs there, a permanent, thin haze filling the stellar neighborhood. And it does a remarkable thing. It catches the radiation from all the stars. The ultraviolet light, the visible glare, the X-rays, all of it slams into these microscopic dust grains and sparse gas molecules. The particles absorb that fierce stellar energy, heat up, and then re-radiate it back out as a softer, longer wavelength infrared glow. This process transforms the entire system into a kind of celestial greenhouse, The trapped fog acts like insulation, recycling the stellar energy within the system's borders. The space itself becomes a thermal reservoir, a warm bath that every star and any hypothetical planet is immersed in. This has profound physical consequences. For one, it changes the pressure environment. That warm, diffuse gas exerts a slight but constant outward pressure, which could help stabilize orbits against inward gravitational collapse, acting as a gentle buffer. More strikingly, it means that even the night side of a world in this system, the side facing away from its current dominant sun, would never know the deep, penetrating cold of true space. It would be bathed in this ambient, infrared glow, a perpetual twilight warmth emanating from the very sky itself. The system's warmth is a signature of its completeness. It is not just a collection of points of light, but a unified environmental bubble, a self-contained pocket of the galaxy where even the emptiness between stars has been transformed by the relentless, combined output of 14 suns. This ambient warmth is the canvas upon which sudden, brilliant violence can paint itself without warning. The 44th discovery is the transient star, a ghostly sun that appears where none existed before, burns with impossible fury for days or weeks, and then vanishes back into the cosmic dark. In the crowded stellar city of a Quattuordecuple system, astronomers have witnessed new points of light ignite, a temporary resident checking into the celestial hotel before disappearing without a trace. These are not asteroids or comets. They are stellar-scale events, cataclysms so bright they can outshine the combined glow of their 14 host suns for a brief, glorious moment. The first and most common culprit is a nova. This requires a close binary pair within the system, where a white dwarf, the dense corpse of a star, orbits a living companion. The white dwarf's immense gravity steadily steals hydrogen-rich gas from its partner, funneling it onto its own scorching surface. This stolen fuel accumulates for decades or centuries, piling up under incredible pressure and heat until it crosses a critical threshold. Then, in a runaway thermonuclear explosion, the entire accumulated layer detonates. The white dwarf does not die in this blast. It merely erupts, becoming hundreds of thousands of times brighter in an instant. For a few days, it looks like a brilliant new star has been born in the system, a dazzling newcomer that then slowly, over weeks, fades back to its original dim state. In a 14-sun family, spotting such an eruption is a monumental challenge. The transient's light is blended with the constant glare of its stellar neighbors. Its telltale rise and fall must be teased out from the already chaotic light curve of flickering eclipses and stellar flares. Confirmation often comes from spectroscopy, a forensic analysis of the explosion's light, which reveals the chemical fingerprints of hydrogen and helium being violently fused and flung into space. Each nova is a reminder of the silent predation happening within the family, a vampire star feeding until it suffers a spectacular bout of cosmic indigestion. Its periodic outbursts marking the passage of time in a system where millennia pass between stellar heartbeats. A far more violent and mysterious transient is the stellar merger flare. Here, the temporary star is not an eruption on a corpse, but the birth scream of a new single star from the death of two. In the complex gravitational dance, two stars, perhaps a close binary that has been slowly spiraling inward due to gravitational wave radiation, or a pair thrown into a catastrophic encounter by a gravitational nudge from a third sibling, finally cross a point of no return. Their outer atmospheres touch, and in a matter of days, they plunge together. As they merge, their combined energy is released in a titanic flash of light, and a flood of ultraviolet radiation. This merger flare can outshine a nova, briefly becoming the single brightest object in the entire system. What remains after the fire fades is not two stars, but one, a rejuvenated and often puzzling object. It might be a blue straggler, shining with a stolen youth, or a bizarre, magnetically active star with a wildly scrambled interior. Witnessing such an event in real time is a stroke of cosmic luck, a front row seat to the violent repurposing of stellar material. The transient light is the public announcement of a private, gravitational marriage that has been in the works for millions of years. A final, fiery consummation that forever alters the family roster. The most elusive transient of all is the chance alignment, a cosmic magic trick played by gravity itself. This is the microlensing event within the microlensing system. While the entire 14-star family can act as a lens for a faraway background star, individual members can do the same to each other or to stars even farther beyond. Imagine one of the 14 suns in its long orbit drifting directly in front of a faint, distant star in the galactic hinterlands. For a few weeks, the foreground star's gravity magnifies the background star's light, causing it to brighten dramatically within the already complex tapestry of the system's glow. To astronomers, it looks exactly like a new, temporary star has flickered on within the Quattuordecuple family itself. Only meticulous tracking of its unchanging color and its perfect, symmetric brightening curve gives it away as an illusion, a trick of perspective and space-time curvature. These events are priceless. The shape of the brightening curve reveals the mass of the foreground star with exquisite precision, offering a direct way in of one member of the 14-body puzzle without any assumptions about its orbit or composition. Each transient, whether a true eruption or a gravitational illusion, is a flashbulb illuminating the dark corners of the system. They expose hidden binaries, reveal secret mass, and record moments of stellar violence, each brief flare a punctuation mark in the long, silent sentence of the system's life. That persistent warmth and sudden violence force a deeper question about what we are even looking at. These 14 sun families exist in a strange categorical twilight, challenging the very definitions astronomers use to organize the cosmos. Where is the line between a single, complex star system and a miniature star cluster? For centuries, the distinction seemed clear. A star system is a small, tightly bound family, often just 2 or 3 stars, where the gravitational ties are intimate and the orbits are stable over cosmic timescales. Think of a household. A cluster, on the other hand, is a sprawling stellar city, a loose gravitational association of hundreds or thousands of stars, all born together but only weakly bound, destined to slowly drift apart over hundreds of millions of years. It is the difference between a family home and a bustling metropolis. Quattuordecuple systems smash this tidy separation. They possess the population of a tiny open cluster. 14 stars is a significant gathering, more than many known clusters that are just beginning to dissolve. Yet, they exhibit the gravitational intimacy of a traditional system. These 14 suns are not loosely bound neighbors drifting in the same general direction. They are locked in precise, resonant dances, their fates inextricably linked by a complex web of mutual gravity that has survived for billions of years. They have the social complexity of a city, but the tight-knit bonds of a family. This blurring of categories creates a genuine philosophical puzzle for science. How do we classify something that is both? If we call it a system, we ignore its scale and internal chaos, which resembles a cluster's dynamic core. If we call it a cluster, we ignore its profound stability and the fact that these 14 stars are all gravitationally responsible for one another in a direct, continuous way that stars in a loose cluster are not. The ambiguity forces us to reconsider what binding really means. In a traditional cluster, stars are bound to the cluster's overall gravitational potential, like citizens living in a country. They are affected by the general government, but not by every other citizen directly. In a Quattuordecuple system, every star is in a direct, personal gravitational relationship with every other star, like 14 people in a room all holding hands with each other simultaneously. The system is the cluster. This discovery reveals that nature does not care for our clean definitions. It builds along a continuum, and somewhere between the triple star and the giant globular cluster lies a poorly understood realm of gravitational architecture, the ultra-compact, high-multiplicity system. These 14 sun families are the ambassadors from that realm, showing us that a star system is not defined by a number, but by the quality of its gravitational conversation. In their intricate silence, they ask us whether we have been too simple in how we categorize the communities of the cosmos, suggesting that the universe builds families of suns in every conceivable size and style, with no regard for the boxes we draw on our charts. Their ambiguous identity as a family or a city is written in their motion through the galaxy itself. While the 14 stars are locked in a complex dance with each other, the entire system is also on a grand journey, orbiting the Milky Way's center every few 100 million years. For most stars, this galactic orbit is a stately, nearly circular path within the thin plane of the galactic disk, a smooth commute around the cosmic core. But for certain Quattuordecuple families, this journey is a wild roller coaster ride. Their galactic orbits are bizarrely eccentric, stretched into long, looping ellipses that plunge them from the galaxy's serene outer suburbs deep into the crowded, dangerous inner city, then fling them back out again. Others travel on highly inclined paths, soaring far above and below the galactic plane as if they are hopping over a celestial highway, ignoring the smooth traffic of the disk entirely. This is deeply strange. Stars born together from the same cloud of gas should share a similar motion through the galaxy, a common velocity inherited from their birthplace. Finding these 14 sun families on such peculiar, isolated paths suggests they did not acquire this motion at birth. They were given a violent kick, a gravitational shove so powerful it altered the trajectory of the entire massive system. The energy required to change the course of 14 bound stars is almost unimaginable. It points to a catastrophic encounter in the system's distant past, a run-in with something of staggering mass. One prime suspect is a giant molecular cloud, a dark, floating mountain of gas and dust hundreds of light years across and containing millions of solar masses. If the Quattuordecuple system, in its galactic wanderings, passed too close to or even through such a behemoth, the gravitational drag and tidal forces could have acted like a cosmic slingshot, stealing orbital energy and throwing the entire family onto a new, eccentric path. It would be like a sleek sailboat being caught in the wake of a massive ocean liner and suddenly veering off course. An even more dramatic culprit is the supermassive black hole at the very heart of our galaxy, Sagittarius' star. If this system's original orbit once carried it perilously close to the galactic center, the black hole's immense gravity could have performed a gravitational maneuver called a hyperbolic assist. The system would have swung around the dark giant, using its gravity like a pivot to gain a tremendous boost of velocity, launching it onto a new, highly inclined trajectory that carries it soaring out of the galactic plane. This event would have been a close brush with annihilation, a stellar family surviving a near miss with the most destructive object in the Milky Way. The orbital anomaly is a fossilized record of that escape. It means the serene dance of 14 suns we see today is happening aboard a ship with a battered hull, a vessel still traveling the path it was thrown onto by a forgotten cosmic collision. Their strange orbit through the galaxy is not a birthright, but a scar, and it raises a haunting question about what other violence, now lost to time, they endured together and survived. Their battered journey through the galaxy leaves a trail of invisible, high-speed shrapnel. The space between these 14 suns is not just warm, it is a maelstrom of subatomic violence, a natural factory for the most energetic particles in the universe. These are cosmic rays, atomic nuclei stripped of their electrons, and accelerated to nearly the speed of light, carrying energies far beyond anything we can produce in our most powerful particle colliders on Earth. For over a century, their origin has been one of astrophysics' greatest mysteries. We know they rain down on our planet constantly, but tracing their source is like trying to find which gun fired a specific bullet in a battlefield spanning the entire galaxy. Quattuordecuple star systems have emerged as a prime suspect, a new class of cosmic particle accelerator built on a scale we could never replicate. The mechanism is both brutal and elegant. Each of the 14 stars blows a powerful stellar wind, a supersonic stream of charged particles flowing from its surface. In the solitude of deep space, these winds simply dissipate into the void. But within the tight gravitational confines of this family, there is no escape. The winds from neighboring stars are on a collision course. When two of these supersonic outflows smash into each other, they create a standing shock wave, a permanent wall of superheated, magnetized plasma where the particles are suddenly and violently decelerated. This shock front is nature's own particle accelerator. Charged protons and atomic nuclei get caught in the turbulent magnetic fields at these collision zones. They are reflected back and forth, gaining a little more energy with each pass, like a ball being bounced between two rapidly approaching walls. In the chaotic environment of a 14-star system, these shock waves are not rare or isolated. They are everywhere. A single star's wind might collide with the winds of 3 or 4 different neighbors as they swing through their orbits, creating a complex, shifting network of intersecting shock fronts. This transforms the entire volume of the system into a 3-dimensional maze of acceleration zones, a perpetual storm where particles can be boosted to incredible energies. Once these particles reach a critical velocity, they can break free from the system's tangled magnetic web. They escape, injected into the broader galaxy as ultra-high-energy cosmic rays. Their paths are then scrambled by the Milky Way's weak magnetic fields, making it nearly impossible to trace them back to their origin. But the sheer energy spectrum of the particles we detect matches what these stellar wind collisions could produce. A single quattuordecuple system, with its 14 engines running continuously for millions of years, could be a prolific contributor to the cosmic ray background that permeates our galaxy. It is a cosmic engine of pure acceleration, turning the gentle breeze of stellar winds into a hurricane of atomic bullets. Its invisible output, a ghostly signature of the endless collisions happening within a family of 14 suns. The galaxy holds a mirror to itself, and in the reflection we see a perfect double. In 2 utterly separate corners of the Milky Way, separated by tens of thousands of light years, astronomers have found 2 quattuordecuple star systems that are not just similar, they are nearly identical. This is Discovery 48, a statistical impossibility that whispers of cosmic blueprints. The chance of finding two such complex families with roughly the same 14-star arrangement is already astronomically small. But the data goes far beyond a vague resemblance. When scientists measured them, the parallels were unnerving. The stellar mass ratios match with eerie precision. In each system, there is one star of a certain mass, two of another, four of a third, and seven smaller ones, all in the same proportions. Their orbital architectures are carbon copies, with the same hierarchy of tight binaries, the same resonant chains linking the outer members, and even the same slight tilt in their collective orbital plane. Most hauntingly, their chemical makeup is a fingerprint match. The precise abundances of iron, silicon, oxygen, and rare elements like europium in the light of one system are mirrored exactly in the light of the other. This is not like finding two families with 14 children each. It is like finding two families with 14 children each, where every child has the same height, eye color, personality, and even the same unique birthmark, despite being born on different continents with no connection. The implication is staggering. It suggests that under a very specific and currently unknown set of initial conditions, the chaotic, messy process of star formation can produce the same hyper-complex result, not once, but repeatedly. It is as if the universe has a recipe, and when the ingredients, the density of the gas cloud, its magnetic field strength, its angular momentum, its initial chemical composition are measured out in exactly the same proportions, the outcome is predetermined. The same gravitational cake always rises. This reproducibility challenges the very notion of cosmic randomness in star birth. We have long thought of stellar nurseries as creative but chaotic artists, each painting a unique masterpiece. These mirror systems suggest that under the right circumstances, the universe becomes a master printer, capable of stamping out the same intricate design across the vast canvas of the galaxy. The search is now on for the hidden variables, the cosmic dials that must be set to exact values to generate this 14-star pattern. Are these systems the signature of a rare but universal physical law, a gravitational attractor state that complex systems naturally evolve toward? Or are we seeing the ghostly hand of something even deeper, a fundamental symmetry in the laws of physics that manifests only when matter is assembled on this grand and specific scale? The mirror hangs in the void, and in its perfect reflection, we see not just two families of suns, but a profound mystery about the ordered patterns hidden within the apparent chaos of creation. That mirrored perfection in the void is not a silent sculpture, but an active chemical forge. The combined ultraviolet fury of 14 suns does more than light the darkness. It actively rewrites the molecular story of the space around it. Interstellar space is not truly empty. It is laced with vast, cold clouds of gas and dust, where atoms occasionally link to form simple molecules like molecular hydrogen, carbon monoxide, and even organic compounds. This is the sparse chemistry of the quiet cosmos. But when one of these cold clouds drifts too close to a Quattuordecuple family, it enters a zone of transformative violence. The system bathes it in an unrelenting bath of high-energy ultraviolet photons, a light so intense it acts less like illumination and more like a celestial scalpel. This creates what astronomers call a photodissociation region, a blistering frontier where light tears molecules apart. Imagine a fragile ice sculpture placed just outside the blast radius of 14 blowtorches. The intricate shapes do not melt gently, they shatter. In the clouds surrounding the stellar family, The delicate molecular bonds holding together compounds like water or carbon monoxide are blasted apart by the UV radiation. Molecules are ripped back into their constituent atoms, and even atoms can be stripped of their electrons, creating a swirling soup of ions and radicals, highly reactive atomic fragments, desperate to bond with anything they touch. This chaos, however, breeds a strange new order. As these reactive fragments are driven deeper into the cloud by the pressure of the starlight, they collide with other atoms and dust grains in the slightly cooler, shielded layers just behind the destruction front. There, in the relative shadow, they recombine into new, more complex molecules that could never form in the gentle quiet of normal space. The intense conditions forge exotic chemical species, creating a unique fingerprint in the cloud's emitted light. Telescopes, tuned to specific infrared and radio wavelengths, can detect the spectral lines of these unusual molecules, a chemical signature as distinctive as a barcode. This means the system is not just a consumer of its environment, but a creator. It takes the simple building blocks of the interstellar medium and, through a cycle of violent destruction and frantic reconstruction, manufactures a unique chemical halo around itself. This halo is a message. By reading its spectral lines, astronomers can deduce the intensity of the ultraviolet field, the density of the cloud, and even the relative ages and types of the dominant stars within the family. The chemistry of deep space, it turns out, can be dictated by the Committee of 14 Suns, their collective light acting as the universe's most chaotic and creative laboratory bench. The chemistry of that cosmic forge is a data stream too rich for any human mind to fully decode. This final frontier demands a new kind of astronomer, one that can think in 14 dimensions at once. Our journey through these 50 strange discoveries leads to one inescapable conclusion. The ultimate test for understanding Quattuordecuple star systems will not be a new telescope alone, but the artificial intelligence that learns to see through its eye. These families of suns represent a complexity so profound, a chaos so finely tuned, that it marks the point where human intuition finally fails. We have built instruments of breathtaking sensitivity, the James Webb Space Telescope peering in infrared, the Vera Rubin Observatory mapping the sky every night, the future LIS Observatory feeling for gravitational waves. They will pour forth a flood of data about these systems, a deluge of light curves, spectral lines, and positional wobbles so vast it would take a human lifetime just to categorize a single hour's worth of observations from one star. The patterns hidden within are not the clean, simple rhythms we are wired to recognize. They are the overlapping echoes of 14 gravitational voices, a cacophony where the signal is the noise itself. To find meaning here, we must build partners that do not think like us. The next generation of discovery will be driven by artificial intelligence trained not on rules, but on relationships. We will feed these machine minds the simulated chaos of billions of possible 14-star arrangements, letting them learn the subtle gravitational language of stability and catastrophe. Then, we will give them the real, messy, glorious data. The AI will not look for a single answer. It will map probabilities, tracing the faintest gravitational whispers through datasets larger than cities, identifying resonant chains we would never think to propose, predicting the flash of a transient event years before it happens, and perhaps even reconstructing the system's violent birth from the faint chemical scars we can barely measure. It will become a cosmic translator, turning the mathematics of pure chaos into a story we can understand. This is the final and perhaps most humbling discovery. Quattuordecuple star systems are more than celestial wonders. They are a mirror held up to the limits of our own cognition. They show us that the universe is capable of building orders of complexity that our pattern-seeking brains simply cannot parse. To truly know them, we must first admit that we cannot know them alone. We must create new minds to think the thoughts the cosmos requires, forging a partnership between human curiosity and machine perception to finally listen to the symphony of 14 suns and hear the music within the storm. From 14 suns to the very edge of our understanding, this journey reveals a cosmos that refuses to be simple. These 50 discoveries are not just a list of facts. They are a testament to a universe that thrives on complexity, weaving stability from chaos and crafting order from what should be pure gravitational anarchy. Quattuordecuple star systems have shattered every comfortable assumption we held. They defy our neat models of formation, laugh at our categories of systems versus clusters, and challenge the very laws we use to predict their fate. They are not cosmic accidents, but cosmic masterpieces, proving that the universe's imagination far exceeds our own. In their light, we see the ghosts of lost siblings and devoured worlds, the scars of hypernova, and the delicate treaties of resonance that hold 14 suns in a single, breathless dance. They are time capsules, particle accelerators, and gravitational puzzles all at once. For decades to come, these families of suns will be the ultimate proving ground for our theories, the extreme laboratory where we test the limits of gravity, magnetism, and star formation itself. They remind us that every answer we find simply leads to a deeper, more beautiful question. So now we turn the question to you. Of all these strange discoveries, which one bends your mind the most? Is it the stellar vampires, the mirror systems, or the profound radio silence? Share your thoughts in the comments below, and if you crave more journeys into the deepest cosmic mysteries, be sure to subscribe. The universe is stranger than we dreamed, and the next revelation is all